No, you don't need that. All right, we are going to go through about 1,100 years of research in about 4 hours. It's a little dense. I've tried to keep it as chemistry light as possible while still giving you guys a real feeling for the fundamentals of what chemistry is and how it affects our lives, really, and the things that we do pretty much every day. All right, switching between. All right, why are we here? Mostly to help you and your staff be a little bit safer. That's the key for all of this. Chemistry, if you receive waste directly, is what making your life unsafe. If you oversee people who do it, it's all that kind of stuff. However, knowing about it really can help you guys recognize some of the dangers. There are key names on labels that can help you recognize some of the dangers and some of the incompatibilities and some of the safeties or things that are safe on stuff. We'll hopefully understand, or at least I'll try and give you an explanation of why some things are dangerous and some things are not dangerous, and why some things are dangerous together but not necessarily on their own. We'll do a brief dive deeper, if you guys want to, into what you can learn from an SDS. Some of that is going to be a little more biology, toxicology, pharmacology stuff, but it can be useful at the end of the day deciding whether something is really poisonous or just kind of a little bit poisonous, and you don't have to worry about it. All right, who am I? I'm the big ugly guy on your screen. I looked vaguely like that about 4 years ago. I have a bachelor's degree in biochemistry. It was a liberal arts degree, so I can quote Chaucer. Please don't ask me to. Then I went to grad school at Purdue University in Indiana, wrote a paper with the following title, which was about as interesting as it sounds. And since then, I've done a series of things, but including 10 years here at Oregon Metro's HHW program. So we are a very busy site, the busier of the two sites that Oregon Metro has. I say this a lot, and we see everything, and we really do. We have a collection, a shelf of oddities, that some of which are truly, truly odd. But they're kind of cool too. Sometimes we only get to see one of each thing, which is too bad because then we don't get a matched set. All right, so my questions to you guys, which you don't necessarily have to answer, but these are my questions about why I'm doing this. What do you already know as a group? It's hard to tell. If you find I'm being too basic as a group, please let me know. If you find that I'm overestimating how much you paid attention to high school chemistry, also let me know that, please. If you have something really specific that you want to learn, please ask me about it. During a break is a good time if you want to do it a little more privately. I do have my email open, which is michael.allen at it was a long time ago for me too, Christina. I'm juggling a couple of screens here, so chat works, email works, or you can just unmute yourself and say something. And please let me know at some point, or at any point really, what I can do to make this class more useful to you. Like I said at the very top, if you weren't all here, I don't have a lot of the rules of the road here. I don't mind being interrupted. I will, by default, sort of lecture at you, so you have to stop me from that. It was what I did in grad school, and I'm hoping to have said I learned from that. Questions you guys have? You won't understand all of chemistry after one class. No one ever understands all of chemistry anyway. My contact info is on the final slide. You can use it from here until the end of time. I'm always happy to answer questions. good. There are no bad questions. So just give me a quick email. I'll usually get back to it in a day or two. And it's a great way to communicate with me. I'm happy to do everything. If I don't know the answer to something, and I may or may not, I am very happy to help you find the answers. We can work together to find out a particular answer. We can try and find out some theory, all those kinds of things I'm absolutely good with. Any major thoughts, questions before we really dive into the chemistry part of all this? All right, let's do it. Oops. All right, there are some things about chemistry we're not going to learn. We're not going to learn about entropy, enthalpy, free energy. For those of you who had chemistry before, you will probably be glad about that. We won't learn about this new, well, I think of it as new concept of hybrid orbitals. You just won't need any of that from a day-to-day point of view. Stuff we will learn. We're going to learn about these little creatures here, moles. You're going to learn moderately deep dive into the periodic table, which I personally think is fascinating. Learn a lot about pH. Learn about some bonds, different kinds of bonds. We'll learn a little bit about organic chemistry, and before you panic immediately, it won't be a whole lot. It's just enough for us to understand what some of the dangers and things are. We'll learn about redox reactions. And really, we're going to learn what any of this stuff means when you're looking at a SDS or a bottle with a label or a partial label, or trying to interpret lab results from something. We at the Metro have an ID of unknowns flow chart that we use. It's we also do a course on that when Metro or when NAMA is live again. Doesn't necessarily allow us to tell what something is, but it's a pretty good way of telling us the hazard class that something belongs to. But we won't go do that today. But if you're interested, whenever we go back to real conferences, it's kind of fun to do. All right, chapter 1. There will be a lot of breaks. If you need another break at any time, just let me know. This, like I said, this is as informal as I can make it, hopefully. These are really the basics. What's an atom? What's an element? What's the periodic table? And what is a mole? All right, we can dive in. Water. Water is actually really, really cool. I mean, like really, really cool. Water is the reason that life as we know it exists. What life literally is, as we know it, cannot exist without some of the molecular properties of water. I know this is kind of weird, but water's really, really cool. Liquid water is denser than solid water. This is incredibly unusual. It's why your beer bottles freeze and break. Poor guy. It has a very high boiling point for a relatively small molecule. And from a biological point of view, this is probably the most important one. It has a very high surface tension. All that means is that when you put a drop of water on the table, it stays as a reasonably coherent little drop. Whereas if you, for instance, put a drop of pure methanol on the table, it would spread out quite a lot. This is important for your blood and capillary action. It's important for a whole series of things that happen inside your cells with transport of chemicals and the like. Water dissolves a whole bunch of stuff. I don't know how you can say more than anything else or less than anything else, but a wide range of things are soluble in water that are not soluble in all sorts of other things. This is treading on the edge of being very geeky, but it has a very high specific heat capacity. That is, when you heat up, you can apply a lot of energy to any unit of water, and it won't change its temperature a whole lot. It does seem like it will, because that's what we use every day, but lots of molecules will change their temperature very quickly if we heat them up and give off that heat very quickly. Water can retain a lot of heat per energy used to it. Sorry, that's really geeky. All right, very, very basics. This is where we start 1100 years of chemistry. What's an atom? An atom, as we understand it today, the simplest possible atom is hydrogen. It has one little blue proton and one electron. It doesn't need any neutrons because the proton and the electron, protons are positively charged, electrons are negatively charged. They're perfectly balanced. Helium, the next possible element, is a little more complicated, not a lot. It has two of each of these things. That isn't going to be true necessarily as we go forward. Sometimes things will, well, lots of things will end up with a lot more neutrons than they have protons. We'll get into a little bit of that later. Rarely going to make a difference to you. What is more important is going to be the number of protons that something has, which is going to determine what element it is, and the number of electrons it has, which is going to determine what it does. Chemistry is all about electrons. They are the currency of the realm. That's what electrons get moved back and forth across things. That's what's causing all chemical reactions that are going to happen that you can see. Electrons can be visualized as floating around in a shell around the nucleus. This is useful in the sense that those shells and have different orbits of shells around the nucleus, and those orbits want to be full. If we think about a reasonably simple group of elements here, we can see that hydrogen and helium have this one inner shell. That inner shell can only hold 2 electrons, but in a perfect world, it wants to hold 2 electrons. Hydrogen is more reactive. You can't see me pointing at my screen. Hydrogen is more reactive than helium because hydrogen is essentially missing an electron. Helium is one of the noble gases, doesn't want anything out of life. I apologize if the anthropomorphizing doesn't work for you. It's my language, kind of way I think about it. This guy's happy. He's got 2 electrons in his only shell, or her only shell, their only shell, that can hold them. There's nothing more they want. Lithium has 2 in its inner shell, but its outer shell can hold a whole 8 of them, excuse me. So it's got 2 ways of thinking about itself, as it were. It desperately wants 7 more electrons, or it would kind of like to give up the 1 in its outer shell that it has, so it could be a little more like helium and just have the 2 inner ones. Carbon is a little more stable than lithium. It's got more electrons in that outer shell. Fluorine is not more stable because it's so close to having filled up here in neon. So there's this weird part of these electron shells that they're kind of less reactive if they're in the middle of wanting more or wanting fewer. They're completely unreactive if both or third or however many 7 shells there are completely full. These aren't really shells. This is a more modern graphic of what these things look like. If it helps for you to think of them as strange little orbitals that are kind of comet-like going around the nucleus. That works. The shells are the way I learned it. I find it an easier way to grasp the concept. Again, if we come down here to sodium, sodium's got this inner shell filled, it's got this outer shell filled, then it's got this third shell that, again, kind of like lithium, is not filled at all. This makes it kind of unhappy with this electron. Or another way to think of it is it really wants another bunch of electrons, another 7 electrons. Silicon, reasonably unreactive, doesn't do a whole lot, doesn't need to do a whole lot because it's about halfway through in its filling of its shells. Chlorine, as we know, is wildly reactive like fluorine because it's so close. It just wants that one other electron in its shell. Argon is an unknowable gas. And so it's not reactive at all. It's got everything it needs to keep itself at an energy state that makes it happy. So what's an element? An element is an atom whose substance all have the same number of protons. So all sodiums are going to have the same number of protons. All lithiums are going to have the same number of protons. What distinguishes a lithium from a sodium is that number of protons. They're the simplest substances available to chemistry. If you're going to break down or change an element, you're not doing chemistry anymore, you're doing physics, and you're talking about radioactivity at one level or another. It's either fusion or it's fission. There's going to be a lot of energy involved in changing an element to something else. It can be done. It's not, we're not quite to the making gold out of lead yet because we don't have a sun available to work in. But the nuclear power plant is, depending on what it's, well, I guess all of them these days, are taking substances and breaking hydrogens off of them, or hydrogens off of them, and transmuting elements. It's pretty much a one-way street at the moment, unless we're talking about fusion bombs, but that's not really a reliable source of energy. So chemistry is not about changing elements. It's about using elements to combine them together with each other, with a, well, there are no other things, in various combinations. Some of those combinations will release energy. Some of them require energy to start, will release energy afterwards. Fire is a great example. Some of them will actually consume energy as they go on. All right, there's a lot of elements. I did email you the periodic table. You don't have to memorize them all. But the periodic table is a work of real genius, like exciting, change the world kind of genius. This guy here, Dmitry Mendeleev, who kind of looks like your mad scientist, although I wasn't really mad, but he was a genius. 100 years ago, in Siberia, started organizing the elements in various ways by what he knew about how heavy they were. Sometimes is their density, sometimes is not. How many protons he thought they had. And he noticed, working off the, you guys can't see that, working off the stuff that other people had done before him, and this is from 1803, so it's a long time ago, that there were gaps in here that we knew about elements like hydrogen and strontium, but there didn't seem to be a 4 in here. There didn't seem to be a 6 or an 8. All these bits and pieces were missing numbers. The periodic table as we know it today, as the copy I sent to you, if you pulled it up or not, it tells us a couple things. It gives this symbol, which is what we humans are thinking of as the element. It gives the atomic number, which is what matters in terms of what the element is, whatever, whether we call it a C, a W, or an X or Y. It's this 6 that is important. All elements have common names. Some of the elements, well, a lot of the elements were not named in English, so that their common name often doesn't, or the English common name often doesn't match the first letter, their main chemical name. We'll get to some of those. Most of them were named in either Greek or Latin. Most of them were named in Greek. And so that's why they have weird names. At least one of them was named in German, tungsten, which is why it has a W, because it was really called wolfram. Don't know why you needed to know that, but there you go. All right. So this is the periodic table of the elements. We'll get into this a lot later. Don't worry about it. Just look at it. It's complicated. This is the most modern, not quite the most modern version. There are actually 118 elements in the most modern version, but they're weird, and we'll never see them. We never have to worry about them. Don't think about them a whole lot. All right. This is a quick little video about Dmitry Mendeleev. It is the only video I have, but it really, frankly, does a much better job of explaining his genius and what I think of as the exciting part of his genius than I was able to do. If you can't hear it, let me know.
Can't hear anything.
All right, hang on a sec. Wonder why that doesn't work. That's an unexpected problem. Sorry about that.
I think sound may have started to come through right when you paused it. I'm not sure.
Okay, let's try this again.
It's very quiet, but we can hear it.
Yeah, I can hear it, but it's very faint.
All right, let me. That sound is up all the way. Don't know that this makes a difference, but turn that up. Let's try again.
There we go.
Is that better?
Yeah, I can hear it.
Okay.
Yeah, that did it.
It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius.
We've lost the sound now.
Comprehensive list of the known elements? Nah.
Is it back?
A spot in Science
Yes.
Valhalla just for making a list.
Okay, hang
The
on.
list of the known elements, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitry Mendeleev, is a bona fide Science Hall of Famer. Why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really. That had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitry was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behave. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
All right. I love that. I think that's the best part of science. It's the best part of learning something, predicting something, having it be real. He didn't know all this stuff, but he knew a whole lot of stuff. And it's the genius in finding it out that I find very exciting, if you can't tell. Right. For those of you who are interested, the only reason you could hear that was putting my microphone next to my speakers. Got to figure out how to do that better next time. All right, we're going to do a deep dive into the periodic table in a little bit. I want to introduce one more kind of fundamental concept about chemistry that we're going to use later. We just need to understand a little bit more about it. All right, concentration in things matters. I didn't know that moles were not rodents. They're insectivores. They have absolutely nothing to do with what I'm about to talk about, but they're a lot cuter than anything else I could find that was a mole. A mole is a measurement of the number of atoms in something. It's complicated. It is 6.022 followed by a whole bunch of numbers times 10 to the 23rd number of atoms in 12 grams of carbon 12. You've heard of carbon 14. There's carbon 11, not much. There's carbon 12. Why is that useful? It's useful because sometimes the number of atoms in something tells us more about its reactivity than if we knew something about the density of the atoms or how reactive each of the atoms was. What it means to us in this class is that it's a dimensionless number. There isn't it's like a dozen. There's not a dozen things until you tell us what the things are. So if we think of 6.02 times 10 to the 23rd as like a dozen, a really, really big dozen, it's just a way of telling us how many things there are. So a 1 molar solution of hydrochloric acid tells us that within a given volume, 1 liter of hydrochloric acid, there will be 6.02 times 10 to the 23rd chlorine atoms. The hydrochloric will have already dissociated to water and hydrogen, or into hydrogen and chlorine. It just stands for molecular. Chemists are just as lazy as anybody else. We didn't want to go around saying 6.02 times 10 to the 23rd every day. We didn't want to say molecular because that's longer than mole. So they stuck to mole. From the point of view of us at HHW, it's a measure of concentration. If you see 2 molar, you know that something's twice as strong as a 1 molar. If you see 12 molar, you'll know that it's 12 times stronger than 1 molar. As a good rule of thumb, if it's dangerous at 1 molar, it's a heck of a lot more dangerous at 12 molar, and you want to treat it with some respect. We just went over this. The one thing that didn't touch on is every once in a while you'll see an N on a bottle, almost always an N that came out of the lab. I don't think it's ever used in a public setting. N stands for normal. It effectively means the same thing as an M. There are some acids, we'll get to them later, where the N doesn't mean that, but it's far more rare than the other way, where N equals M. Again, it's just a measure of concentration. 12 is lots more than 3. Kind of all you need to know. If you see something 3M, it's not enough to tell you much until it tells you 3M of what. 3M of calcium chloride, salt solution. It's not terribly dangerous. 3M of hydrochloric acid is something you're going to want to pay attention to. So while the concentration is important, it's not the be all and end all. This is a good time for break. Anybody hate taking a break at this time? Anybody? Because you're a very quiet group.
I'm okay with the break.
Okay, let's do a 10-minute break. So we'll come back at 11-minute break. We'll come back at 9:45.
Okay, not a problem.
All right, if this is not working for anybody or you have something you need to do differently, I will be here by the computer. I'll check my email. You can use the chat directly to me. Just let me know. I'm open to all sorts of suggestions. Thank you. We'll see you guys in 11 minutes. Hey, Justin, we're taking a quick break. We'll be back live for the show at 9:45. All right, 9:45, at least by my clock. We'll give everybody a couple minutes. Anybody back? Hard to ask if you're not back, because then you wouldn't be able to answer the question.
I'm back.
All right, thank you. All right, is this working for anybody?
Yeah, this is working well. Thank you.
Okay, good. Okay. Just want to make sure we're not leaving everyone out in the dark here.
I know it's weird presenting to a screen.
Yeah, it's the first time I've done that. The screen doesn't have a whole lot of feedback, and but it's, you know, these are the times we live in, and this is the way we make this work. And in its own way, it's kind of fun to do something new. I'm 57. It's been a long time since I did anything new. All right. Coming up, a medium shallow dive into the periodic table. If you cannot tell that I'm fascinated by the periodic table, I hope to convince you in the next section. So hoping to learn to use my keyboard. All right, the periodic table. It tells us all sorts of things. It tells us some of the really basic things. It tells us some really complicated things. It tells us its structure has meaning in and of itself. It tells us what things are metals. It tells us what things are metalloids, which is just a way of saying quasi-metals. And it tells us some things that are not metals. It is, however, not the only way to visualize the periodic table. You can break it into chunks with some weird little outliers. You can do this, which is a way of dealing with the metals. If you look at this weird structure here, this part here, the pink and the whatever color that is, are this part here, and they kind of, in the standard periodic table, fit into a little slot here, but they kind of don't, which is why they're separate. This is a periodic table organization that fits them in. This one is too. This little chunk here is the same as this little chunk here. This one makes no sense to me at all. And this one has pretty pictures, so it's kind of cool, but otherwise it's just a standard periodic table. The point of all that is there's a couple of different ways to visualize all this. I think it really only matters if you're really into the weird congruent parts of the, oh, I don't need this on. God, I've gotten so used to wearing this. Sorry, I wear that every day, 10 hours a day, because I don't have an office. And now that I have an office, I don't have to wear it. Anyway, so these things are just kind of weird in their own right. All right. Why do we care? I mean, they got a copy on the wall. We can look on the wall and see what it is. We care because it'll tell us things about stuff that'll come through the program. Whether they'll pose a danger or not, it'll tell us, and we'll get into this, why lithium and water don't mix. It gives us a feeling for why fluorine, hydrofluoric acid, causes horrible burns. We may get into this at the very end, but you really won't feel them very much. Generally speaking, it won't be the burn from hydrofluoric acid that will kill you, but the fact that fluorine here will bind to all sorts of positive things in your body, and you'll die of heart failure because you'll be missing a series of ions in your bloodstream. And while you will have this horrible burn on your skin, what the hydrofluoric acid is really doing is running around in your system and stealing magnesium and calcium from your system. Your heart, your nerves, your muscles all need those to function. A big enough spill of hydrofluoric acid that may take a chunk out of your thigh is big enough to kill you. The periodic table gives us some feeling of why that sort of thing is true. Periodic table is formed of groups, which are the columns, and periods, which are the layers, or the rows, I guess, in the modern spreadsheet world. They all have some similarities between them. Is that the way I want to say that? A group has similarities between the group. A period has similarities between the periods. The periods of the table, going from H to HE, for instance, in the simplest possible period, is a filling up of those electron shells that we were talking about earlier. The reason this table is arranged as it is, and the reason this distance between the H and the HE exists in this table, is that single shell question that we had at the very beginning, where the H has just its one little proton, but it's also got only the one electron in one shell. Helium has its two protons, two neutrons, and more importantly, from the period point of view here, it has two electrons and it's filled up a shell. This second period is about filling up another electron shell. Third period is about filling up a third electron shell. Each of these has 8 electrons. That's trivia. You don't need to know that. 4 and 5 are about filling up another shell. 6 and 7 get complicated because there's a shell here, but there's also a shell here. This is why these guys are tricky to put in here. Also true that lanthanum and actinium don't particularly fit well into this group. That's periods, though. Any questions beyond the very basics? What is a period? It's about filling up shells. Does that make sense to everybody? Anybody? Hearing no dissent, I'm going to go with yes. Okay, thank you. Groups are more about their chemistry or their reactivity, something called their electronegativity. We'll get into that in a little bit more. Groups usually have names. They're kind of what are called trivial names. It doesn't mean that they're trivial. It just means that it's not a complicated scientific name or something. They also have numbers. The numbers of groups are considered non-trivial. The names are trivial. I don't know. I can't explain that. So group 1A are all these elements that, from whichever shell they're trying, are all missing one electron from that shell. These guys here, the alkali earth metals, are all things that, excuse me, let me go back to that. These guys have one electron. in their outer shell, whatever that outer shell is. These guys have 2 electrons in their outer shell. These 2 here have 2 electrons in their outer shell. We're going to ignore these guys. They make no difference to us in the real world. These guys here, these guys are missing oxygen. Group 6A are missing 2 electrons to be complete. This makes them more reactive than 4A, 3A, but 7A is where we're getting into really reactive chemicals. If you think of it, everybody, well, I'm going to stick with that. Everybody wants to be over here. All the chemicals want to be a noble gas. All of these are gases. They all have full outer electron shells. This is a brand new one. It's one of the newest elements on the table. I think it's like 4 atoms of it that existed for a nanosecond, something like that. But it's that Mendeleev thing here. We know a lot about it because of where it is on the table. You'll have heard of all of these. Radon, I just said, is really stable because it has all its issues. Why are we worried about it? That's a question of radioactive radon. That's, from my parochial point of view, that's a physics question, not a chemistry question. That's because it's an isotope of radon. It would have the same chemical properties as non-radioactive radon. It would just be radioactive. Xenon, krypton, and argon and neon are all in neon lights. They all make different colors of neon lights. That's a question of getting them super excited chemically so that they start throwing off photons. But it's not a reactivity of their chemistry question. These guys are really happy. They're stable. They're thermodynamically stable. They're stable in a fundamental physics sense of being completely aligned with their outer electrons. So charge being balanced by the proton charge. There are enough neutrons to keep everything together and stable. They're happy. It's really hard to break these guys apart, even radioactively, or even in physics in a sense. These guys in here, this middle chunk, these are all called transition metals. And you can take years of courses in transition metal chemistry alone. Generally speaking, from an HHW point of view, these are important. Obviously, they occur in a lot of things. But the ones we see are things like mercury, cadmium, zinc, iron. They're all less reactive than anything in either group 1A, 2A, 5A, or 6A or 7A. But that doesn't mean they're not dangerous. We'll get into heavy metals and metals in a little bit. But these are all metals here. These guys here are quasi-metals, or on the edge of being metals. Some of them, like titanium and aluminum, clearly metals. Metals being defined as something that conducts electricity, something that conducts heat, something almost always shiny, and something that you can deform. That is, if it's a liquid, it's hard to deform something. If it's a gas, it'll expand to fill the appropriate space. A metal you can squish around. Gallium, you literally can hold in your hand and watch it melt. It's kind of cool. It's not toxic in any way that we know of. I mean, you don't want to eat it, but it's not toxic by holding in your hand while it melts. Sorry, this is thallium, not titanium. These guys here, in many, many ways, are what life is about. We couldn't have life without water, but all of the moderately reactive things like oxygen to the really stable things like carbon are what life's compounds are built out of. DNA is built out of all these things. All your proteins are built out of all these things. And that's because there's a little bit of reactivity here, not a lot. There's a little bit of stability here. Well, there's a fair amount of stability here. And they have lots of points of attachment. We'll get into all that in a little bit. So here we are again, groups are coming down. These are things with similar properties. With new shells beginning to fill up, the periods are about filling up the same shell within each period. What does this look like kind of for real, as it were? Here's you can't see that. Here's hydrogen, here's lithium, here's sodium. They all have one electron in that outer shell. Beryllium, magnesium, they've got 2 in the outer shell, but they'd really like to have 8 in the outer shell. So, okay, we won't get to that yet. Transition metals are the same kind of way. They're in here. The life chemicals or elements, as it were, not quite so much boron, but definitely carbon and the nitrogen family, are things that have room for more electrons, but don't desperately need them. And they aren't desperately imbalanced like these guys are over here. Fluorine and chlorine, we know are both very reactive, and it's really because they're just so close to having this shell filled, that they're so close to a thermodynamic is not quite the right word, but it's a good way to think about it. Stability that they will do a lot of things to get there. Trivial names: noble gases, halogens, alkali earth metals, alkali metals, transition metals. We talked a little bit about this. They have formal designations. The formal designations are the 1A, the 2A. We talked about that a little bit. You'll hear it'll be a chemist, or it'll be somebody trying to be a chemist, talk about period 2 elements or period 5 elements, or the period 5 elements that are in 4A, which they can say because they know that tin is there. I had to look that up. I'm not that much of a chemist. Generally speaking, from our point of view, again, we're interested these groups out here. With the exception of the heavy metals, these won't be RCRA items unless it's technetium or mercury. These are the reactive items and things we care about. If you can't tell, this is my favorite periodic table. Elements all want to be noble gases. Noble gases are stable, fundamentally stable. You'll see that they're filling up, again, you can't see that. They're filling up these elements, these shells here. He's filled up the first S2 shell. He's got a second S shell here, and he's got a P shell. These guys have 3 S shells, 3 P shells. Goes on and on and on. They're F shells. The F shells are these guys here in the lanthanum series. But they're all full. They can't accept any more, or else that would be a new shell. They desperately, it's really, really hard chemically to wrench any electron out of any of these outer shells here. It takes a ton of energy to make anything happen that would make helium give up its outer electron or radon give up its outer electron. We talked about this. All right, these guys, just to go back to where we are going to start here. We're going to talk about alkali metals. Alkali metals have a couple of properties. as you might guess, they tend to be more basic. They tend to be more alkali when in water solutions. The metals themselves are not creating the alkalinity as much as their reaction with water is creating the alkalinity. We'll get into that with pH, but do be aware that when these guys react with water, alkalis tend to result from that reaction, whereas the elements in 7A will result in acids being part of that reaction. Not generally speaking at all, absolutely, well, it's exponential really. Water reactivity. Hydrogen, really not very water reactive. You can mix hydrogen and water all day long, not very much happens. Start mixing lithium with water, it gets pretty exciting. If you enclose the reaction, what'll happen is that you'll end up with a bunch of helium gas or hydrogen gas, and you'll be getting, and that hydrogen gas is coming from the water, not from the lithium becoming hydrogen. Hydrogen gas, that reaction between the water and the lithium is generating a lot of heat. If you contain that hydrogen heat gas, it'll burn, cause an explosion. Sodium generates even more heat. Potassium generates even more heat. Rubidium, cesium, francium, if you throw them in water, you get a really, really large explosion. Like really, I don't think anybody can do it with francium because it's just doesn't, it's not stable enough. But cesium and rubidium, throw a little bit of them into water, it's very exciting. It's also very exciting to throw lithium and sodium into water. That's the sort of thing chemistry students do on their off hours. We don't go to parties, we just throw things in lakes. We don't anymore because we're environmentally conscious about all that. But before we knew that we weren't supposed to throw things in lakes, we may have done so. So what's happening? What are these things doing? Why? What's going on? If you look at water here again, water is sharing some of these electrons. Oxygen is sharing a little bit with hydrogen. Hydrogen gets an extra electron because it's sharing with oxygen. This lithium comes around and rips off, well, yeah, it displaces this hydrogen, well, or this one, but don't think of it that way. Displaces this hydrogen, forms lithium hydroxide, hence our base chemical. And every 2 times it does that, as every 2 atoms that do that, generate hydrogen gas. Hydrogen gas, as we all know from the Hindenburg, is flammable, it's explosive. It is a combination, it's a diatomic molecule. That is, hydrogen gas exists not as one hydrogen at a time, but as 2 hydrogens sharing their 2 electrodes. This process of the lithium ripping this off and displacing it generates a lot of heat. That heat causes that hydrogen gas to ignite, explode, if you contain it. And that's true of all of the alkali metals, all the way down the road. Going back here a little bit, the reaction that lithium does to create lithium hydroxide is call it a 6. This is about a 12. This is probably a 36. These guys are in the hundreds, maybe thousands by the time you get down to here. I just made those numbers up. It's just a growing reactivity that is exponential as you go down that group. So what's the deal here with sodium? I mean, sodium, I put salt in my water all the time. It doesn't explode. What you're doing, though, is you're putting sodium chloride in your pasta water. You're not putting sodium in your pasta water. And you wouldn't want to, because it would get exciting fast. It really would explode. But when you put salt as you buy it from the store. It's sodium chloride, it's not sodium. And that allows these chlorine atoms here to intersperse themselves with the water, while the sodium also does that. It effectively has neutralized the sodium. That is, it's done its reaction with the outer electron of the sodium shell. If there were, and there is, lithium chloride, I don't know how it would taste, but it would do the same thing. If you put lithium chloride in your salt, in your pasta water, it would not explode. Cesium chloride, cesium chloride's weird. Cesium is a liquid at room temperature, and it's radioactive, so let's not go there. Does that make some sense of why putting salt in your water is not causing it to explode, but putting pure sodium in your water would cause it to explode? Any questions about that that aren't as clear as they might be? Okay. All right. All right, we're gonna move on to halogens, which is far other side of the table. Let's go back a couple of slides up first. To a lesser extent than group 1, group 2 is going to do similar things. And this is why these kinds of, we don't see a whole lot of beryllium, but magnesium metal, pure calcium are water reactive in a DOT shipment as well. These things will have similar, a little bit, well, a lot less reactivity than sodium, but magnesium is trying to do the same thing, to fill its outer shell, just like sodium is. Calcium the same way. And they can steal those electrons from water when they're mixed in together. Same idea, they generate some hydrogen gas, they are water reactive. Okay. Halogens. So halogens, as a reminder, we're way over here now. We are just so close to being a noble gas that we could taste it. These guys are just like, oh, wow, I got to do it. The funny thing about this filling up of your outer electron shell is that the electron shells that are smaller are more energetically stable. That is, it's virtually impossible to rip an electron out of that outer shell of helium. It's almost impossible to rip that outer electron out of the shell of neon. It's just really difficult to do it with argon. It's really moderately difficult to do it with krypton. And so the stability here of these outer shells is going up. Well, it's going, let's think about it this way. It's going down as we go down the table. What that means to the halogens is that their reactivity is going to go up from iodine. We're never going to see either of these guys. Up from iodine to fluorine. Iodine is reasonably reactive with all sorts of things. Fluorine, as we know, is highly reactive with all sorts of things. It's one of the very few things that is so reactive it'll leak through glass. They tend to be poisonous, where the alkaline metals do not tend to be poisonous. Part of that is that they are so reactive with things that even if they're not going to create an acid or a base, they're going to strip your body of something that it needs because they need to be bound to anything else. They're all oxidizers. We'll get into that a little bit, even though none of them have oxygen in them, obviously. And they tend to form ionic bonds rather than covalent bonds. We'll get into that in a little bit. But these tend to be weaker bonds because as much as they want to grab onto something, they're kind of always looking for something better to grab onto. It's not a great way of thinking about it, but we'll get to that in a minute. Oops. In this reactivity, so the reactivity is going up here. These all form acids. Remember, these guys all form bases. These halogens are all going to form acids in water. And all the acids are going to be stronger acids as we go down the reactivity. It's a little bit kind of counterintuitive. You would think that the more reactive components would form a stronger acid. It isn't quite the way it works, given that acid strength is measured by the number of hydrogen ions in the solution, not quite so much the number of halogens ions in the solution. Another way to think about it maybe is that the hydrogen fluoride is so reactive that those two things are going to stick together better. The hydroiodic acid is not quite so reactive, so they're not going to stick together as much. They're going to separate. That's going to leave, and we'll get into this in detail, that's going to leave more hydrogen atoms out in the solution. That's going to be a stronger acid. They're all kind of cool looking, really. They're all, 3 out of the 4 that we generally talk about are gases at room temperature. They're so light that's true. Fluorine and chlorine are gases even at low temperatures, even at very low temperatures. Bromine, which is this kind of strange but very cool orangey color, even at room temperature in a vial, kind of shifts between being a gas and a liquid. In a cold enough room, you'll see just a little bit of vapor above the liquid. In a warm enough room, you'll see very little liquid, even if it's exactly the same vial, which hasn't changed any of the amount of bromine in it at all. Iodine's really cool in the sense that it'll sublimate. Sublimate is just a really fancy word for something that goes from a solid to a gas without becoming a liquid in the meantime. The most common example that we've all seen of this is carbon dioxide, fog. You put a piece of carbon dioxide on the desk, and it immediately starts to create this sort of water vapor thing. It's really cool. The thermodynamics of this happening are fascinating. Not relevant to this class in the slightest, by the way, but they are fascinating because it avoids a whole phase change. And it's weird how they do that. Anyway, but we don't need to know that. All right. So in a way, these things, the fluorine, the chlorine, the bromine, a little bit less for the iodine, aren't really reactive on their own all that much. That is, if we left them in a glass, they wouldn't do much of anything. A little bit true of the earth metals too. They just kind of sit there. From our point of view, these things are reactive when we add water to them. Water is life, so life matters, especially to us. So that's where they get their reactivity from. So here's an example of pKa means something very similar to S or to pH. Don't worry about it. Some of these you can't measure the pH for. These things, this is a relatively weak acid. I mean, if it were a pH, it would not be a RECRA acid. Hydrochloric acid, much stronger acid. By the time we get down to here, and these are all exponentials, by the way, just like pH, we're talking very, very strong acids. But on their own, they're just going to sit there in the vial. Any questions about the two far ends? That is what I think of as the RECRA ends of the periodic table. Speak now or forever hold your peace. Cool. All right. All the stuff in between these two kind of areas here are metals or metalloids, almost metals, kind of metals, metal wannabes. And even some of these things are metals. Metals conduct electricity and heat. You have to do that to be a metal, to get into the metal family. The reason that these guys are metalloids is that they don't do one of those two things. If I remember this correctly, germanium conducts heat but not electricity. Polonium, don't remember. But these are all metals. Metals can be a problem in a number of ways. What do we know about metalloids, the wannabe metals? They're generally poisonous. That is, if you see things that are outside of this, and this is true of elements, by the way, not necessarily compounds, elements or compounds being combinations of different elements. These kinds of things on their own are not going to be wildly poisonous. Fluorine will be wildly poisonous as soon as you mix it with water. That is, as soon as it comes in contact with you. On its own, not so poisonous. These guys here are going to be poisonous just on their own. That is, they will react with something in your body. Doesn't have to be water, doesn't have to form an acid. It'll be toxic right then and there. That'll be true of some of these guys as well. I mean, silver, for instance, gold, mercury. They're so-so conductors. Some conduct heat better than electricity. Some conduct electricity better than heat. They tend to conduct electricity better as the temperature goes up. Strangely, a lot of these, especially silicon, germanium, beryllium to some degree, are what's used to dope semiconductors and to make them better conductors at different temperatures. So the great desire, the great invention that still has to be found is a room temperature superconductor, because of this property here, where these guys get better as they conduct temperature, as the temperature gets up. It's not going to be one of these guys, probably. It's going to be something else, something way down in here. The rare earth metals are probably where we're going to find a room temperature superconductor. Non-metals are, as I said, kind of the stuff of life. They are, the noble gases are non-metals by virtue of being gases. Most of the halogens are not metals. You have to go way down on the table to get anything even vaguely metallic. Hydrogen, carbon, all these things, they're not metals. They may have the occasional metallic property, but they're not metals. Except for hydrogen, all these things can form multiple bonds. We'll get into that in a little bit. But except for the group 17, except for the halogens, they're not desperate for those missing electrons. And they do still kind of like the electrons they have, so they're not ready to give them up, like the alkali earth metals, sodium, lithium, or the alkali metals and the alkali earth metals, sodium, lithium, and magnesium. That's pretty much the periodic table. It is a really shallow look at the periodic table. Let me get back to my good periodic table here. But what I'd like you to be able to take away from this, you don't have to have one on your wall. It doesn't have to be on your coffee mug. But be aware that the table is going to tell us things about these elements. It'll tell us, even when they're in combination with other things, you can learn some things about them. We're not going to see a lot of pure elements in HHW, although we did have a guy a couple of years ago who was collecting every single element till his wife went ballistic and said he had to get them all off the shelf. It was a nightmare to dispose of them all, if you can imagine. Cost a lot of money, and he was very sorrowful to see them all go. He was an interesting guy. I'll give him that. When he brought us 5 pounds of sodium and oil, that was an exciting day. Anyway, sorry, no more stories. Takeaway. These things are water reactive. These things are water reactive. These things get more and more water reactive as you go down this list, as you get heavier, as they begin filling in more shells. These guys over here are the be all and end all of elements. They're perfect. Their social media accounts are all up to date. They're all good. They want for nothing. They're beautiful. They're fine. These here, the halogens, are reactive. They want to get that last electron into each of their shells here. The closer these guys are to the top of the table, the more reactive they are. The more things you see, if you don't know the name of something, or if you have the name of something in front of you, the more Fs, the more Cls, the more bromines it has, the more reactive it's likely to be. We'll get into this a little bit later, but the more likely it's going to be an oxidizer, the more likely it's going to be an acid when mixed with water. There's a reason that all our pool chemicals have these things in them. They kill stuff. That's what the pool chemicals want to do. There's a reason that all salts have one of these guys in them. These guys like to bind to things. The stuff of life is over here. It's in this sort of moderately reactive, but kind of reactive way. This part of the table is beyond the scope of this class. That's probably worth knowing in and of itself. These guys here in the middle are all the metals, or a lot of the metals, excuse me. You'll see some of them. A lot of their reactivities are going to be a little more individual than can be predicted by their placement in this table. But none of these are good for you. That is, eating any of these is not recommended. Having them, seeing any of them in a chemical compound that comes to your facility or that's something you're going to want to evaluate, all of these guys will say poison at some level or another. Some of them, helpfully, mercury, for instance, will say poison and corrosive. There's a bad guy here, bad actor. Some of them are really cool. Osmium is what we think currently is the densest element available to us. Densest not being its little 76 here, but the amount of osmium you can put into any particular space, grams per cubic meter, for instance, or grams per centimeter. Osmium is as dense as we think something, as we currently can get something. Iridium and platinum are the next on the bunch. I don't know why you needed to know that, but it's just kind of cool little chemistry facts. Right, any questions on the periodic table? I'll be astonished if there aren't any. So if you have a question and you're unsure about it, you can just put it in the chat to me. Kind of feel that if you guys don't have any questions, either I've done a spectacular job, which I always doubt, or I haven't done a good enough job in pointing out things that are questionable. All right. All right. Cool. Let's take another break because we're going to go to a whole different kind of thing here. We're going to talk about some real chemistry, not just the theory of chemistry. We'll talk about some elements. Why do they combine? How do they combine? What does the P and pH mean? Nothing, by the way. And what are oxidizers and how do oxidizers work even when there's no oxygen involved, which they do a whole lot of time. So let's, what do we think? A 10-minute break? Does anybody object to a 10-minute break? Let me put it that way.
Sounds good.
All righty, let's do it. Let's come back at 10:40 and we'll talk about pH, which is also really cool. Thanks, guys. Or if I was supposed to pause this while we take a break, because it's going to be a pretty dull recording here. 10 minutes of nothing. Well, nobody told me to.
That's what editing software is for.
Yeah, there you go. Thank you. This could use a lot of edits. All right, are we back? Are we all back? If you're not back, raise your hand. Sorry. Chemistry humor. All right, I think we'll just assume that everybody's back already. All right. Chemistry is all about combining things. The bits and pieces we just talked about, the periodic table, the what are called valence electrons, those electrons in the shells around things, are all interesting, or at least they're interesting to me because I'm a chemist. But it's the combination of stuff that is really interesting. It's the combination of stuff that makes chemistry magic. It's a combination of things that when you mix two different things, you get a completely different color solution. In a way, it's kind of like pizza. I happen to love pizza. I happen to love chemistry. I had to get pizza in here somehow. The pizza comes in a lot of different types, obviously, but it contains elements that are kind of a permanent part of the pizza and elements that are not quite so permanent a part of the pizza. In some ways, and I'm stretching here because I love pizza and I love chemistry, but in some ways it's like covalent bonds and ionic bonds. And you'll have to bear with me here as we make this analogy work, maybe. All right, lots of elements combine with lots of things. Lots of elements combine with themselves. Lots of elements need to combine with themselves. Hydrogen on its own doesn't really exist outside of in solution with something. Same is true of oxygen, nitrogen, and chlorine. On their own, they combine with each other to share electrons to fill up those outer shells. And they're gases almost always. Not always when things combine with themselves. All four of these guys are gases. But life would be boring if it was just a one-to-one combination of all the elements. What makes chemistry interesting is A, that they don't always combine with each other, and B, that they can combine in multiple different ways. And these are really some of the simplest possible combinations. You can do all sorts of weird stuff. You can combine elements that are hugely different in size. For instance, nitrogen is about 14 times larger than a hydrogen. You can combine elements that are even bigger. Fluorine has a relative size of 27, aluminum 57. All these kinds of things are possible, and these are just inorganic bits and pieces. It almost always takes energy to combine some elements or energy to break them apart. This is true even when you're putting salt, sodium chloride, into water. What you're doing is you're taking the sodium and the chloride, which are right here together, and they're perfectly stable on the shelf. In the salt shaker, they're not going anywhere. assuming your house is dry. Put them in water and they're going to separate. It doesn't feel like it takes energy to do that, but as I'm sure you've all noticed, if you heat up the water and you put a lot of salt in it, it's easier to quote unquote dissolve the salt in the water. You're adding energy. The hot water is adding energy to this dissolution. If in fact you took a glass of water, put a lot of salt into it, say more than it could hold, started stirring, adding no heat, in about 10 or 15 minutes, you'd notice that the glass that you're stirring the salt water into is cooler than it was when you started. The making of salt water, the creation of salt water, is an endothermic reaction. It takes energy to make it happen and produces no other energy. Burning wood is exactly the opposite. Burning wood takes some energy to make it happen, but it also then gives off a heck of a lot of energy. Endothermic and exothermic reactions happen all the time. They are not, one's not better than the other. I don't know why that came to mind, but they both have the purpose that they serve. We are generally in the HHW world more concerned with exothermic reactions. We're generally concerned with exothermic reactions in our world because we're around things that we don't want to burn. That is, producing heat in our HHW world is generally seen as a bad thing if it's going to set off the gasoline or the acetone or the isopropyl alcohol that is right next to you. Endothermic reactions we just don't worry about as much because they're not likely to cause as much trouble, but they happen all the time. We had, I guess it's about 5 years ago now, we bulk all our flammables in a hydraulic crusher. They go into a 55-gallon barrel, and then we cap that, let it sit for a while, ship it off. I came into the bulking room once at the end of the day, and one of these 55-gallon barrels full of flammables of various sorts has condensation on the side of it. And it was a good, we have a nice heat gun, a nice flare heat gun. It was a good 10 degrees cooler than the rest of the room, an endothermic reaction. We never did figure out what it was. But we didn't have to panic because it wasn't an exothermic reaction. That is, it wasn't 10 degrees hotter than the rest of the barrels in the room. So exothermic reactions are ones we worry about. Sadly, they don't come with little labels that say this is going to be an exothermic reaction. We kind of have to learn those. But again, one of the takeaways from this course I'd love you guys to get is that this word exothermic is an indication that the temperature is going to go up at the end of whatever it is that's happening, and you want to be careful. So exothermic, so exo is greater, thermic is heat, reaction is reaction. In the formation of water, you can take hydrogen and oxygen in gas form, add some electricity, you get water. You don't get that energy back. That is, there's no heat coming off all that. You've just created water. This is one of the reasons why water is so valuable in our world, is that it takes energy to create. There are wonderfully, enormously complicated structures in the world, especially in biology. It's always biology, but I'm a biochemist by training, so I tend to use examples like that. This is a relatively simple molecule in organic chemistry, and we'll learn this later. You'll be very excited. All of these little vertices, these edges, are a carbon atom. You can't see a single thing I'm doing. All these little things are carbon atoms. And only when there is some non-carbon or non-hydrogen attached to them, sometimes when there is it spelled out. This guy down here is a representation, not a picture, of DNA. This little double spiral thing, each of these little balls is a molecule, hundreds and hundreds of thousands of combinations. Sometimes in biology, even this is too complex a structure. So we get a picture like this, which doesn't look like biology in the slightest, or chemistry. But each of these little spirals is part of this, which is a protein, which is an enzyme actually. And each of these little spirals has a name and a differentiation. This is, I think, a spiral A here. This is a B here. Don't remember the rest. So that we've come up with ways of simplifying the views of enormously complicated reactions. We're not going to have to do that here. There are major fundamental types of bonds, of ways that this guy connects to this, that this little dot connects to this, that this spiral is formed out of things connecting. There are hydrogen bonds. These are, generally speaking, important biologically, but they're critical biologically. Hydrogen bonds and water are fascinating. I took a year-long course on the structure of water. These are very weak bonds. These are like the fresh toppings that go on the pizza. They're the last things that happen. They're not so much the least important, but they're the most fragile. The first thing that comes off the pizza as the delivery guy goes around the corner. There are metal bonds. Metal bonds can have lots of different structures to the same bond. What's an allotrope? Allotrope's a really big word. An allotrope is one version of something. For instance, carbon. When carbon bonds with other carbon, lots of other carbon, you can get a couple of different things. One of the things you can get is a diamond. Wonderful, sweet, the structures are all, or bonds are all nicely aligned. But to get to that, you had to start with this lump of coal, a chunk of pure carbon, as it were, and create that diamond. But both of those things are carbon. One, well, they are allotropes of carbon, and allotropes happen a lot. We won't worry about them so much because although they have some different chemical characteristics, that is, diamonds are largely unreactive, lump of coal creates heat, they're not something we see a whole lot of. It's an industrial chemistry process. If you are taking a lot of CG waste or VSQG waste, you may come across some metal allotropes. If you do and you have questions about them, again, shoot me an email. I'll happily walk you through trying to find an answer to what you need. Generally speaking, we won't see a lot of those. These two we're going to see a lot of: covalent bonds and ionic bonds. Ionic bonds, I'm going to go backwards in this one. They kind of trade electrons. I'll give you one of yours if you give me one of mine, or I'll give you one of mine, but you have to kind of pretend to fill up my outer shell while I give it to you. Covalent, these guys tend to be weak, easily disrupted bonds. Ionic bonds are often salt bonds, and not just sodium chloride, but salt in general, which has a chemical meaning we'll get to in a minute. But they're disrupted by things like putting them in solution, where it turns out that the hydrogens and the oxygens from water can go around and serve a similar purpose to the ionic bond that was being formed in the first place. Covalent bonds are effectively a permanent bond. They can be broken. They are broken all the time, but it isn't going to be as simple as just putting something in water. You're going to have to add some energy to break this covalent bond and to create a new one. What does all that mean? Let's get back to water. Like I said, water's cool. I was told to leave this out, but I can't. This angle here between these three things is one of the most important angles in life. I would argue it is the single most important angle in life. This angle of 104.5 allows all sorts of things to happen in the middle of it, and it creates the structure we know of as proteins, as amino acids, as allows carbohydrates of certain structures to interact with certain other things. Water's cool. Water's unique. These guys, though, are sharing their electrons. That is, when you put water in water, water doesn't break apart. It's still this three atom, 1, 2, 3 molecule. It does that because hydrogen is pretending that water is helping it fill its outer shell, which it is, because now it's got 2 electrons out there. This hydrogen the same way. Oxygen is happy because it's got its outer shell filled. That is, it has 1, 2, 3, 4, 5, 6. Now you can't see that. 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. One of the reasons that the shell thing doesn't work as well as other models of electrons is the visualization of these 2 lone pairs here. I mean, how is it that we can have these little guys floating around here? These little guys are supposed to float around here when they bump into each other, get in the way, all that kind of thing. Hugely more complicated than that. But that's one of the reasons not everybody's happy with seeing these as spheres. Sometimes they're happier seeing them as globes, not even globes, sort of tear-shaped orbitals, hybrid orbitals. So this is a really, really stable molecule. Something is going to have to come rip this bond apart, and these 2 electrons are this bond. We can add energy. We can add a lithium, as we saw, one of the alkali metals, and it's strong enough. Its need for that extra electron is stronger than hydrogen's need for it, so it's going to rip it off. But it's pretty stable. That is a covalent bond. Salt, on the other hand, or sodium chloride, to be specific, has a problem. That is, the chlorine only needs 1 electron to fill its shell. Sodium has 1 to give, and it would kind of like to get rid of it because it'd be more stable. if it could just live with a full outer shell. So what happens when you get salt is instead of sharing an electron, they'll give one to each other. Well, the sodium will give one to the chlorine. That makes the sodium happy in its own way, happy being thermodynamically stable, because it now has a full outer shell or series of polar orbitals, excuse me. Chlorine is thermodynamically stable because it's got its outer orbitals full as well. These two now can coexist pretty well because they are both thermodynamically stable, one of them having, you can think of it as giving, I think it's probably more, well, none of them is more accurate to say, but probably chlorine stole the electron rather than sodium giving it up. Not that there's a court of law that's ever going to matter, but there you go. This one needed it more than this one wanted to give it up. These kinds of bonds are ionic bonds. Like I said, they're weak. These, in effect, these sodium and chlorine are coexisting. They're not, sorry, I have really crappy hands, but if we think of as water as being tightly meshed like this, the sodium and the chlorine are kind of just living together. They've each given up something, or in a sense, but they're not really bound. They're just happier next to each other. A covalent bond is more of we're not only living together, we've got some commitment here, and we're sharing some resources. For whatever reason, well, not for whatever reason, because sodium is so close, that is, it's right here, it really wants to get down here. Chlorine is really, really close. It wants to get full here. They can't share. They're toddlers. These are 1.5-year-olds, 2-year-olds, and it's either mine or I didn't want it in the first place, and you can have it. We certainly can't play with it together. There are all sorts of salts. Chemists tend to cringe when we say salt, unless they're cooking, in which case it's okay. Salts are all ionic bonds. They're almost always water soluble at some level or another. And they're always a combination of a metal, even if you don't recognize it, and a nonmetal. Baking powder, sodium bicarbonate. Oops, sorry. The sodium is the metal. Sodium bicarbonate, the bicarbonate, we'll get to that later, is the nonmetal. Rust, ferric chloride, ferric oxide, either one, is a metal, the ferric, the iron, and a nonmetal, the oxygen or the chlorine. This is just salt around a tequila glass. This is sodium chloride. I don't know why I put that up there. Ionic bonds result in something called cations and anions. There are sadly no dog ions. I'm a dog person, not a cat person, if you feel the other way. Oh, good question from Dave. Let's go back to that. Sorry, Dave, I wasn't watching the screen. Question is, are the electrons orbiting in the same plane like the solar system, or are they in a three-dimensional orbit? The answer is probably neither. That is, it's certainly not like a solar system orbit, because there isn't enough room for all the things that need to orbit around the nucleus. We don't think that it's like the solar system in the sense of the Oort cloud, the sphere of stuff around the solar system that has stuff orbiting in there either. Because if we go back to these lone pairs are probably just kind of like these guys, orbiting in a weird sort of a pear shaped, teardrop shaped, but a three-dimensional hybrid orbit that is being influenced by a couple of different things. Even, let's do this one. The electrons are being pulled towards this positive here. They're being pulled towards this positive here. If we could flip this on its side here, what we'd have is a ball here, a ball here, and a ball here. They are also floating in an orbit kind of like this, sort of this three-dimensional pear-shaped orbit, and they're being influenced by being pulled towards this, being pulled towards that. So they're kind of floating. They want to go this way, but then they want to go this way. Then there are the other electrons, these lone pair electrons, are keeping the electrons in this bond from going over here. That is this lone pair, which isn't quite sitting here doing nothing, but it's sitting here being negative. The electrons are negative. They don't want to go towards anything negative. And there's negative electrons over here too, so they don't want to go over there. So they're constrained to this non-circular orbit-y thing. We can revisit that at the end. I can pull up some, I think I can do it now. Let's find out. Can you guys see the screen that says sick of the 40-minute time limit?
Yes.
Okay, good. Oh no, that's YouTube, sorry. Stop it. So they kind of look like this, and let's forget the math. But they're floating around in this sort of weird three-dimensional space. And then they transition between these two spaces. And if you visualize that in a more complicated molecule, where this center is another proton, it becomes strange fast. And people have real trouble figuring out how to visualize it. But it's the only way we can have these guys here on this be available for a bond while still thinking of this as a shell out here. Nobody likes to get rid of old ideas, even when they're not perfect. So we use the concept that these four guys here are forming a shell around this centerpiece, even if maybe quantum dynamically they're not really doing that. Hopefully that helps, because any other questions beyond that, we're going to have to pull up some math that I don't completely understand, and then I'll look stupid.
No, that helped, Michael. Thank you.
Okay, yeah. The answer is it's weird. It really. And this model, you can't see me do this model, fails when questions like that get asked. Dog ions. We don't have dog ions. At one point, I had memorized the Greek reason that we have cations and anions, but I don't remember at the moment. It has to do with the rising and setting of the sun. Cations are something with cat not being cat, but Greek for towards the west or the east, don't remember now, and being the other. So that's why we have cations and anions. Anyway, when we, sorry, got lost there. When we have ionic bonds, we end up with a cation and an anion. The anion has the extra electron. So it's in a non-neutral state. So it's got a negative charge on it that is compared to its base state. The chlorine here has this extra electron, which gives it a negative charge compared to this chlorine here. The sodium has a relatively positive charge. That is, it now has an extra proton compared to the number of electrons that it has. Chemically, we can't change the number of protons. That's a physics question. So we have a relative positive charge here. So this is a cation. This becomes an anion. All the ionic bonds, you can see where the name comes from, end up with something with a cation and an anion. They don't necessarily need to live together to be happy, because what happens when they get into water is that the sodium, remember, has a positive charge, has an extra proton, or has a proton that is unmasked by an electron. It's going to hang out with these little lone pair electrons here because it's got a positive charge, negative charge here. The chlorine is going to hang out in this little space here because it's got a negative charge, and these two alone-ish positive charges are going to help it hang out and be happy. Water is what's called a polar solvent. That is, it has a highly negative center here, slightly positive centers out here. We'll get to that more in organic chemistry, but you should know that that's true. We won't touch on this much, but one of the things about the periodic table as it's arranged in this form is that electronegativity tends to increase as we go to what is the right of our screen. Electropositivity tends to increase as we go to the left of the screen. What that means to us, again, largely ignoring the middle here, is that things at this end, that is leaving aside the noble gases, are kind of going to want to form ionic bonds with things at this end. Unlikely to be covalent bonds because the electron negativities are so great and so low at this end. If we remember from the very beginning of the periodic table here, this guy has one free spot in his shell, in his hybrid orbitals. Helium has none. Lithium has one free spot. That is, it wants to fill up that second shell. Not one free spot, excuse me, one free electron. Beryllium has two. Fluorine has one free spot. Oxygen has two free spots. Carbon well, nitrogen has 3 free spots. Carbon has 4 free spots. What that means is that they're going to be able to form this many bonds. Now, given a trick in, let's just accept it as truth, that these metals here these 3 metals, and these 3 metals only largely, will tend to form ionic bonds, whereas these guys here, the quote unquote stuff of life minus this, will tend to form covalent bonds. But carbon can form 4 covalent bonds. Fluorine is unlikely to form a covalent bond, like lithium is unlikely to form a covalent bond, but they can each only form 1 at a time. You won't see things like sodium chloride 2. That is, you won't ever see a sodium with 2 chlorines hanging off it, because there just aren't that many electrons to go around. If we remember from the beginning, electrons are the coin of the realm here, and it's just impossible to generate that many electrons in that kind of an atom. Now, you will see oxygen dihydride, commonly known as water. There aren't ionic bonds, but oxygen, because it needs 2 electrons here, can form 2 bonds. Oh, I did remember this stuff. Okay, did put this in. This is why we have cations and anions and no dog ions. Still sad. All salts are a metal and a nonmetal. We saw this before. Sodium is the metal, carbonate, nonmetal. Iron oxide, iron, nonmetal. Table salt, sodium chloride. I actually hate tequila, but it is one of the things with the most other chemical parts to it, which I'm sure gives it the smell and the flavor that it has. But all of these are covalent bonds. Only the salt around the edge. So you'll see these in your when you're looking at labels and the like. You'll almost always, by convention, not by any other reason, the metals are listed first and the non-metals are listed second. So this is copper sulfate. This is copper sulfate. One of the things you'll see when you're looking at a label of a bottle is it'll have a count of water behind it. So this is copper sulfate. It's kind of grayish, not very interesting. Copper sulfate pentahydrate is a dry chemical that has 5 water molecules surrounding the copper sulfate. They're not bound in any way. They're just nearby. And as you can see, this can result in 2 completely different looking things. They're the same compound, and if you put both of these in water, you will end up with exactly the same thing. But these are not allotropes because it's the exact same element and compounds. There's just water added to this, which gives it this wonderful blue color. This trick question is a weird one. It's one of the things that makes science kind of weird. This is a carbohydrate. The reason a carbohydrate is called a carbohydrate is because when they first began exploring these, and this is early 1800s, they thought that the carbon was a metal and there was a bunch of oxygen surrounding it, just like this copper sulfate pentahydrate. They thought there was a bunch of water surrounding the carbohydrates, when in fact, glucose looks more like this, a series of very covalent bonds with some hydrogen bonds. Any questions, thoughts, comments? How really cool that is? Generally speaking, when you're looking at the label, the pentahydrate part, the heptahydrate part won't make a whole lot of difference to you. It has a little bit to do with how soluble in water it is. But if it's poisonous before it was a pentahydrate, it's going to be poisonous after it's a pentahydrate. It'll react as everything does before it was a pentahydrate. You'll see it a lot in drugs, and it's a way to get them into solution. Lots of all of the active drugs will either be a hydrate, a pentahydrate, or a hydrochloride. Like for instance, triaminic hydrochloride is one of the antibiotics, and that's just a way to get them into solution. It's not telling you that this is hydrochloric acid with an antibiotic on it. It's confusing, but it's just a way to get them into the water so they'll be biologically active. Yeah, let's go back here. So this guy doesn't look like this because this is changing the oxidation state of this copper a little bit. That's as much as you need to know about that. Maybe more than you need to know, frankly. Inorganic chemistry doesn't have as many functional groups as organic chemistry, which is up next, by the way, after a break. But here are some that you should be aware of and pay attention to, really. Almost anything ending in ATE is going to be an oxidizer at some level or another. All of the things ending in nitrate are going to be oxidizers. The sulfates and the phosphates are oxidizers, or can be oxidizers, but not in a sense that we're really going to worry about the oxidation part of that reaction. Anything with a nitrate is going to be an oxidizer. The trick is you've got this A is important because the nitrites are not always oxidizers. So it's worth just frankly memorizing this nitrate means NO3. It's going to be bound to something else if it's a salt, and all of these are salts. You'll notice there's the silver nitrate, lead nitrate, hydrogen, which is a metal by courtesy because it's at that end of the periodic table. So all of these are your classic salts. They're all going to be oxidizers. Sulfate is just going to tell you that it has sulfur and oxygen on it. Phosphate, phosphorus and oxygen. Carbonate, carbon and oxygen. Inorganic carbonates, that is, if there's not a whole lot of words or letters or anything before or after this carbonate, are generally speaking chalk. They may be various kinds of chalk, they may be various colors of chalk. They're generally non-toxic. They're generally non-reactive. They're generally not very interesting. We're generally going to ignore them. All right, pH. pH is a big deal in our world. It's the second test we do if we have an unknown chemical come in. First test being, does it react with water? pH can tell us a lot of things. I mean, merely from a regulatory point of view, it can tell us if this is a characteristic waste or not. pH, as we think of it in HHW, is only true in water. So that is, as much as you might like to think you can dip a pH strip into gasoline, acetone, whatever. doesn't really work. You can mix your gasoline with water where it doesn't really mix very well. Shake it up, and you can try and get a pH from sort of the water phase as it's still separating. But that's not really a pH. pH is something in water that has dissolved in the water. It can be another liquid. It doesn't have to be a solid, but it has to have dissolved in the water. There are ways of getting a pH equivalent called a pKa or a pKb of non-water solutions, and you may have a pH electrode in your lab that can do that. That's a great thing. Those numbers are comparable in their dimensions, but they're not exactly the same. All right, so what? As we know, pH goes from 0 to 14. 14s are highly alkaline issues. pH 0, highly acid. There are mineral acids, there are organic acids. Corrosivity is a slightly different thing than pH. And why is the P so little? Start with the only interesting part here. No, I'll take it back. It's all interesting. The P is little because no one knows what it means. It started as the opposite. And nobody really knew what that meant either, in that, except that P was supposed to say something about the concentration of the H. Now it means the decimal logarithm, the inverse logarithm of the concentration of hydrogen ions. This is a touch counterintuitive, maybe even a lot more than a touch counterintuitive. The higher the acid level in something, the less H plus activity there is. That is, if you have a pH, let me rephrase that, sorry. The higher the pH, the lower the number of H's involved. What's equally true is that the higher the pH, the more OH's, OH minuses, anion, cation, are involved. As much as we like to think about pH as being all about this H, it's really about the interplay between these two ions, the H and the OH ion. The log scale of it just means it's exponential. pH of 14 is 10 to the 14 times more than a pH of 0. This produces huge ranges and activities, so that it's worth being careful if you're talking about a pH of 2 and you say to yourself, okay, you can deal with that. For whatever reason, the boss allows me to handle that. A pH of 1 is 10 times more, 10 times less or more, depending on which way of the ions involved. So it's a lot like the earthquake scale. You want to be very careful in the difference between the 1 and the 2. Well, a 2 is not 1 plus 1. This is 100 times different, or 10 times difference, excuse me. So pH of 2, pH 12.5. These are either RICRA or DOT, depending on which you want to use. There's two levels that matter to us, really. One is more of a DOT issue, which is the rate at which it corrodes metal. That's obviously because DOT likes to put things, or likes us to put things, in metal drums, and it wants to know how quickly it's going to get out of them. The other is a question of how much biological damage, or what it's going to look like in water reacting to something else. We interpret that when it hits our skin as biological damage, but it doesn't have to be. Hydrochloric acid as a concrete cleaner, there's no biology involved there. It's a question of how much of the dirt is it going to pull up off the concrete by virtue of that chlorine pulling things away. Back in the good old days, people used to taste these things. You'll notice that vinegar tastes a little sour. Bitters in fancy drinks taste a little bitter. That's because vinegar is an acid. Bitters tend to be hydroxides of various things. Acids tend to react with metals where bases don't. This is not completely true, but it's a rule of thumb. Bases tend to react more with fats and oils. They do something called saponify them, and they do that to proteins too, whereas acids don't. Acid names often, not always, but often, end in IC. Hydroxide is a very, very good indicator that what you're dealing with is a base. It may not be a very strong base, but it's a base. In the world of biochemistry, a base as strong as 8.2 can be a problem to a biological system. Obviously, it's not even a REC base in the slightest. Acids feel, sticky is the wrong word here, but they're not slippery. When you get, and don't do this, but when you get a base on your fingers, and this is what we used to do in chemistry, it is kind of slippery. It's not oily, but it's more slippery. A lot of that has to do, by the way, with the fact that they're reacting with the fats and oils in your skin, which is why we don't do that anymore. And this is reacting in a different way with some of the proteins, and it's getting rid of the oils. Anyway, all these things are rules of thumb that you can take away and say, okay, God, I remember Michael said something. You don't have to remember what it was, but I'd love it if you would remember that there are differences in how the acids bases feel, what their names might be. Taste would not be something I would use. I threw that in there just for fun. Mercury's weird. I mean, mercury's kind of fun weird. If it weren't so toxic, it would be really fun weird. Mercury's corrosive. We know that. We have to stick an 8 on anything in a mercury in a drum. But yet this guy's putting his finger right in there, and if you're old enough, you played with mercury as a kid. You kind of threw it around your fingers. We were young and foolish. Because mercury's not in water. It doesn't dissolve in water. You can't really make it dissolve in water unless you use aqua regia. And even then, it doesn't really work because the acids in the aqua regia are what is going to determine the pH. It's called mercury, not because Hg has any hydrogen in it at all. It comes from I can't even pronounce this, but archivos, which is liquid water, silver water. So don't be fooled that this H in mercury has anything to do with its corrosivity. Mercury as a whole is corrosive to metals, but it's not because of the H. It's corrosive because it corrodes most metals at a rate greater than or equal to 0.25 of an inch per year. That's the DOT definition of corrosive. So even though you can't take the pH of metal, you've still got to stick an 8 on it in the drum. You got to stick a 6 on it in the drum because it's toxic. But be aware that H has nothing to do with it. It's not a proteinization question. It's not a question if you stick it in water of the OHs and the H's being part of the issue. Mercury is weirdly corrosive without having a pH. Fun, but weirdly corrosive without having a pH. All right, no one really wants to be a real chemist. Chemists want to do things, but they don't really want to be them. But there are cool ways you can sound like a chemist. If you want to talk about pH, that's great. pH scale goes from 1 to 14. There are acids and bases, more acids really, that have what's called a pKa, which is a ratio of the protons to the anion concentrations that go below 0. And some of these are called superacids. We'll get to some in a minute here. But if you, chemists generally don't talk about pH, we generally talk about pKa or pKb. The numbers are different. The idea is the same. pKa's lower than 0 are very strong acids. pKa's approaching 12, 13, 14 are very strong bases. You'll see these numbers sometimes in an SDS. They're not, well, I don't know if they're supposed to be there or not, but think of them as a placeholder for pH. They mean a similar kind of a thing. They can, however, be negative, and they can be above 14, although that's staggeringly rare. But lower down still means an acid. Higher up, above 7 means a base. Lower than 7 means an acid. Same idea as possible. That's the math involved. You'll see them, know what they are. They relate to the molarity and sometimes the normality of the acids. Acids, by definition, are things with low pH, but it's not really what it means. Acids are where the hydrogen ions, the cations, are leading the reactivity, the activity in the solution. There aren't enough anions, the OH minuses, to do much. Not, we all know acids that are safe. Vinegar is relatively safe. We have to be aware, we touched on this earlier, have to be aware that things, medications, organic molecules as a whole, anything with a long name, almost anything with a long name, but the things with the longer the name is, the more likely it is to be organic. A lot of them have HCl after them. That does not mean you need to pack them with uric acids. All it means is that it has this little chunk of HCl on the end of it so that that H can leave and it can get whatever the rest of the molecule is into solution, so it'll be biologically active. So as you're reading label for methadone HCl, recognize that this HCl is not the same as the muriatic acid, concrete cleaner, pool chemical HCl. They're the same elements, but the concentration of this is as near 0 as possible. So it poses no corrosive risk. The risk with methadone HCl lies entirely in the methadone and the biological activity of the methadone, nothing in the HCl. You'll see this a lot on a lot of pharmaceuticals. Don't be fooled by it. They're acids, but they're not Recker acids. They're not acids that we're going to worry about putting a DOT level 8 on. They're not going to have a GHS warning for corrosivity. Biologically, they can be an issue. But from our point of view, our very narrow sort of at the edges of chemistry, the Ricker edges of chemistry point of view, they don't matter. They matter, they just don't matter to us. As a rule, mineral acids, and these will be acids with shorter names, or with a metal in the front of the acid, in the front of the name, are stronger than organic acids. I don't know if you guys remember the name or the movie Alien, where the organic acid is eating through the metal. Let's just hope it's some sort of organic superacid, because that's generally not true. Mineral acids, with one major exception, tend to be not as toxic as organic acids. That isn't to say that the fact that it's eating away at your skin is not toxic. It's just not causing a systemic issue with your body beyond the pain and all the really bad parts. Hydrofluoric acid is that one exception. Hydrofluoric acid is so horrible, as it were, as it is, because it's not a very strong acid. It doesn't necessarily hurt when it hits your skin. It only begins to hurt when it gets through the skin layer, and that's the H part of this, the acid. But by that point, the F part, the fluorine, has begun to travel through your system and bind up all the magnesium and the calcium that the rest of your body needs to survive, for your heart to beat, for your nerves to work. So that's toxicity part of hydrofluoric acid that is separate from its corrosivity part. Does that make sense to anybody, everybody? HF is a bad one. It's one when we're training people, we try and spend extra time with, because it just, you can spill armor etch on yourself, or the glass cleaners, glass etchers, and you'll say, well, it's not so bad. I'm not going to write an incident report about that. But in fact, you really do need to. It's a very big deal. You need to wash it off. You need to get calcium gluconate on there. You need to bind up those fluorine molecules as quickly as you possibly can. Sorry, my 2 cents on hydrofluoric acid is bad. It is a mineral acid. It's not very strong. It is toxic. Mineral acids, and this is generally not true of organic acids, tend to be oxidized, or can be, not tend to be, I apologize, can be oxidizers as well as acids. Nitric acid is one. Strong sulfuric acid is another one. Organic acids are far more likely, leaving HF aside, than mineral acids to be toxic as well as corrosive. Oxalic acid is a classic example. It's not a very strong acid, but it is toxic, poisonous, flat out, as well as being an acid. It is, in fact, much more toxic than it is corrosive. If you want a chemistry word that you can take home to your kids or partners or boss to prove that you listened and learned something, you can use the word monoprotic. Monoprotic means that it has one proton to give away. Lots of acids are monoprotic. HCl is monoprotic. HNO3, nitric acid, is monoprotic. Sulfuric acid has 2 protons to give away. It is diprotic. Why does that matter? Remember the N's at the very beginning when we were talking about the little cute moles? The only time the N is going to matter in any way that's different from an N is if it's not a monoprotic acid. That's enough. Take that home with you. Tell your boss you know about monoprotic acids, and then leave the room before they ask too many questions. But you could say that, I know that normality matters for things that are not monoprotic acids. There you go. You learned something. Phosphoric acid gives up 3. From a RECRA point of view, we're only going to worry about the first one. because the pH at which they give those up is different, but you will see 3 normal phosphoric acid in a jar sometimes, where you might say to yourself, well, how's that different than 3 molar phosphoric acid? It's not. Just don't even worry about it. It's going to be rare. Think of it as molar. You're good to go. What does it mean? It means this. It means it's giving up this electron at different points of OH minus activity in the solution. All right, once again, inorganic acids, mineral acids, they're both the same thing. They mean the same thing, tend to be the strongest acids. They tend to come from all sorts of places. I've seen hydroiodic acid not come from a meth lab, but it came from a VSQG. And once it came from okay, it's a good story actually. We had these 2 nice young couple come in, 20 somethings. And they said, Grandpa was an insomniac and he was trying to help himself make sleeping pills. And we brought all his stuff in. And so there's hairs on the back of all of our techs' necks going up and saying, all right, chem lab stuff, be careful, be careful, be careful. Well, Grandpa was an insomniac because he was making meth in his lab, in his basement. And one of the things he needed to do that was hydroiodic acid. The couple came back a couple of weeks later, and we did not tell them that. We just told them that we had found the stuff in the lab, we disposed of it. Thank you very much for bringing it in. But that's where you'll see hydroiodic acid. Hydrochloric acid is also known as muriatic acid. They're the same thing. Muriatic acid is just one particular concentration of hydrochloric acid. You'll usually see it as 20 with a little degree symbol above it. That's 20 BOM. That's a very old concentration measurement. It's just hydrochloric acid. It's just as bad as hydrochloric acid, but it's just hydrochloric acid. Nitric acid shows up from household chemists, school cleanouts, or labs, VSQG labs. And the guy who was collecting elements because he used it to dissolve a lot of his elements, whatever. Hydrofluoric acid, again, this is my personal bugaboo. Glass etchers, aluminum cleaners, all of these things contain hydrofluoric acid. If I were king, which would be a bad thing, we would label these a lot more aggressively. One of the ways that, because they'll hide hydrofluoric acid, it'll be ammonium bifluoride. Still, as soon as you put it in water, it's hydrofluoric acid. They'll say things like burns that are not immediately apparent. Whenever I see that phrase in my mind, that tells me I'm looking at hydrofluoric acid, probably, and I should be on the lookout for it. Oxidizing acids, there aren't too many of these, but they are something that you, certainly HHW, need to be very aware of. Nitric acid is the classic one, especially strong. Nitric acid, 70% plus, is a very strong oxidizer as well. You'll want to keep it away from all organics. Chromic acid tends not to be quite as strong an oxidizer, although I think it's strong enough that if I were king, again, bad idea, but if I would ship it separately. Skip ahead here for a second. Strong sulfuric acid, that is 97%, all those kinds of things. When you get strong sulfuric acid, you'll almost always get it from a VSQG. Double check your own internal tables or the hazmat table to see how it's supposed to ship. Some sulfuric acid with some other things in some concentrations will require an oxidizer sticker as well. Perchloric acid is really, really nasty. Strong acid, it's a super strong oxidizer. We'll talk a little bit more later if we have time. Memorize that word. Memorize this word is bad. Memorize this word means that you need to pay attention and find a resource, whether it's an email to me, you're a chemist on the hazmat team, somebody once told me to pay attention to perchloric acid. I'm asking a question. There you go. That's all you need to take away from that, but it is out there. It's a super, super strong oxidizer that will cause fire with sawdust all on its own, kind of thing. Organic acids tend to be a little bit weaker, tend to be a lot weaker. Lots of the biological things beyond even the drugs, although I guess you could call folic acid and pantothenic acid drugs, are called acids. It's just a way to get them into solution. Again, doesn't mean much. There are RCRA organic acids, but again, most organic acids tend to be poisons rather than corrosives. Amino acids are just barely acids. Nucleic acids are barely acids. You can't have proteins without these. You can't have DNA without these. You can't have fat without those. Guess that would be too bad. Folic acid's a vitamin. You need citric acid. It's a vitamin as well. So the word acid isn't always bad. Isn't always good either. There are some strong organic acids. Sulfonic acid, almost anything that ends with sulfonic is going to be a strong acid. It is one of the strongest, except for this one, organic acids out there. It's very strong. I've never seen this in real life. Hopefully none of us will ever see it in real life. If I were to tell you, if you wanted to take a class on chemistry for non-chemists and you wanted to learn something about this picture here, I would tell you to look at these Fs. Those Fs are fluorine. Anything with a fluorine is reactive. Anything at all. May not be immediately hazardous to life and health, but it's going to be reactive. Carbon is more of your framework. Oxygens can be reactive, can be oxidizers, obviously. Beyond that, that's all you need to know about this molecule, except that there's enough fluorines that you need to get some help for it. Acetic acid is not terribly interesting. It's a carboxylic acid, which is this functional group here. We'll get to that later. Sometimes you'll see it in some food uses and some cleaning supplies, enough to give it a pretty low pH. Glacial acetic acid is the same compound. And notice these H's here, carboxylic acid group. H is here, carboxylic acid group. The thing about glacial acetic acid is it doesn't have any water in it. It's a liquid in and of itself. It is flammable, it's corrosive, it has a very high vapor pressure, so you don't want to open the bottle and sniff it. At very low temperatures, it'll form crystals. These are not terribly reactive crystals, but it will form crystals. Any questions about acids? That may be probably is more than you wanted to know about acids. And yet there's more good stuff. All right, let's move on to bases. Bases are things with a pH above 7. Bases are things where this anion here, activity is predominating, where it's making things happen. Household bases are pretty normal. I mean, some of them are even kind of high. Milk of magnesium makes your stomach feel better because it's reacting with the gastric juices that are up here, creating roughly a 7. Bleach, as we all know, is a base. It's also an oxidizer. Oven cleaner, sodium hydroxide, generally speaking, is a very strong base. Bases have their own pKa version. It's called a pKb. If you can't find a pH of a base and you can only find a pKb, that same sort of dynamic still exists. That higher the pKb is, some spam call. The higher the pKb is, the higher the pH is going to be, and you can think of it as a recra base, even if you don't have that pH number. Always better to be safe than sorry. If you do have a pKb and it says it's 7.5, well, it doesn't mean the pH is 7.5. It generally means that it's roughly in the middle there and is probably not a recra base. Well, it's certainly not a recra base. It may be poisonous, but it's not a recra base. Inorganic bases tend to be named after the metal part that is the first part of their salt component, as it were. It's called a conjugate. Sodium, lithium, so sodium hydroxide, lithium hydroxide. Lye is just sodium hydroxide. Ammonium hydroxide occurs a lot. Carbonates are technically bases, but they're not very strong bases. Carbonates, especially sodium bicarbonate, is something you can use as an emergency come on, Michael, brain. Equalize either bases or acids. If you put it on, it'll bring the pH back down to about 7 or 8, depending on what you put it on. These are great neutralizers. There's the word. Sodium bicarb, calcium carbonate are not as good as that. They're not terribly dangerous bases. They're not terribly reactive bases, but there are elements in the bicarb that make it a much better neutralizer on an emergency basis if you just spilled battery acid or something and you don't have what oil gator or acid gator around. Dump some bicarb on it. It will work. It will bubble. It'll look kind of evil as it's bubbling, but it's just throwing off carbon dioxide as it's bubbling. Give it a couple of minutes, measure the pH. If the pH, say you put it on battery acid, is still low, put some more of the bicarb on it. If the pH is still high because you put it on a lye solution, put some more on it. It'll bubble, it'll look evil, but it's doing its thing. I wouldn't recommend these two as that, but this is a good emergency neutralizer. Organic bases don't happen a lot. They do happen, amines happen. They tend to be more biologically active than recra issues. They're almost all derivatives of ammonia. Again, it's like the HCl in the drugs or in vitamins and things. A lot of the amines are there to get them into a system where they can be active. They're not necessarily dangerous on their own. Oxidizers and reducers. Kind of think we should take a break. How does everybody else feel? Let's do it this way. If anybody wants to take a break, there we go. Let's take a break. All right, it is noon. Let's do this first. My plan was to go all the way to 1 without lunch and then just do lunch afterwards. Is that okay with everybody, or do you guys want to break for an hour for lunch and then go back to the rest? Either one works for me. We probably need some sort of a vote thing. I don't know, or else I'll make a decision.
I'd prefer to power through.
Power through, I hear. Short break. All right, let's power through. Let's do a short break. We'll come back at 12:10 and we'll get out of here early-ish. Cool. Let's do it. All right, we'll see you in 10 minutes, guys. All right. If you're not here, say something. All right, we got 50 minutes left. We got way more than 50 minutes worth of work. So I'm going to power through some things. If it happens to be a topic you're super excited about, please let me know. We'll try and slow down for it. These classes are always too long. I need to do a better job vetting myself. Anyway, here we go. Oxidation reduction reactions. We will go slightly fast through this, but not completely. I'm never going to learn. All right, sorry. The word redox is what chemists use to describe this kind of thing. It stands for reduction and oxidation. You can't have oxidation without reduction. You can't have reduction without oxidation. Unfortunately, for the word anyway, you can have oxidation without oxygen. Oxygen is an oxidizer, obviously, but things can be oxidizers without having any oxygen involved. As I said at the very, very beginning of this, chemistry is about electrons. Reduction, oxidation reactions are all about electrons. Oxygen, like I just said, is a really good oxidizer because it comes in and steals electrons or grabs electrons or whatever metaphor you want to use. The oxygen ends up with the electrons, the iron doesn't. The iron has been oxidized. What that really means, it has, yes, okay. The iron has been oxidized. The oxygen has effectively been reduced. That it has taken on more electrons and lowered its net electronic charge. The iron in iron oxide has been oxidized, and you can think of that as another word for being increased or becoming more cation-like. These redox reductions are the bane of first and second year chemistry students because it's not always easy to find where the electrons are, where they're going, and why they got there. But in its simplest form, it's all about those electrons. The iron here is getting oxidized. The oxygen is getting reduced because it's grabbing some electrons away from this iron in order to bind to it. It's another example here. If it's not about oxygen, why worry about oxidizers? I mean, it's not, what we're really worried about is fire, right? Well, yes and no. Because in HHW or hazardous waste in general, we're really dealing with the edges of chemistry. It's not, the simple things are not what concern us. It's what's happening to produce visible, often dangerous, and almost always unwanted results. So when we talk about oxygen as an oxidizer, we're not really talking about the oxygen. We're talking about something that is an oxidizer. It happens to be adding oxygen to the system, but it isn't necessarily the issue involved. This is a classic bleach and brake fluid. Oh, this is, didn't leave this. This video has no sound, so you don't have to worry if you can't hear it. But if you guys have HHW customers who come to you every day with bleach and brake fluid in their cars in exactly the same container, tossed side by side, I always want to bring them in and show them these kids being stupid, because this is what you get with bleach and brake fluid. The SDS is very clear on oxidizers. This is it's a good symbol. I think it's got this nice O for the oxygen, but it's got fire too. Section 2 is where you'll see this kind of statement of the SDS. I guess you don't have to memorize these numbers, but it might be worth thinking that the hazard statements in the 270s are worth remembering. They all relate to oxidizers. 271 is probably the one you want to pay attention to the most, because it's not just an oxidizer, but a strong oxidizer. If it says 270, it'll always says 271 and 272, as far as I can tell. 271 is really, don't get this near heat, don't get this near organics, pay attention to this. Don't mix it with acids either because of the heat of reaction. Going fast here, and I apologize for this a little bit, but peroxides are something that we all worry about in HHW and hazardous waste in general. Peroxides are just tricky. They're a combination of the two things we just saw here. They're an organic and they're an oxidizer. Peroxides are not all organic peroxides, but there are very, very few exceptions. In organic chemistry, this R doesn't mean anything other than a reactive group. So a peroxide is anything with a reactive group, which can be as simple as hydrogen, an oxygen bonded to another oxygen, and another reactive group, which can be as simple as a hydrogen. If these two R's were H's, it would be hydrogen peroxide, be a strong oxidizer. It would also be a peroxide. All peroxides are oxidizers. Not all oxidizers are peroxides. The per at the beginning of a word is a pretty good clue that something might be a peroxide. It's not perfect, but it's worth saying to yourself, hey, what's this per at the beginning of peroxymonosulfate mean? It means it's a peroxide. We're going to worry about organic peroxides a little bit more than peroxides for the obvious reason, that they can form crystals. Crystals, peroxide crystals, not all, but all organic peroxide crystals are shock sensitive or friction sensitive. Larry Sweetser is teaching a class right now, I think right now, on things that go boom. These will be featured prominently in his presentation. I do a presentation on things that go boom. They're featured very prominently. Some peroxide crystals can form in what you don't think of as peroxide compounds. For instance, THF, the tetrahydrofuran, is not a peroxide, but it can form peroxide crystals. This furan is a highly reactive organic chemistry group. Time is not a friend to any chemicals or any of us or anything maybe, but chemicals on a shelf that have been there 2 days are way less dangerous than chemicals on a shelf that have been there for 2 decades. Doesn't matter what it is, really. These guys, if the longer they've been there, the more chance they have of going bad. I don't want to step too highly on Larry's presentation. You're going to worry more about old things with metal on metal caps, because the friction involved in the metal on metal can set off a peroxide explosion. You're going to worry about anything that says anhydrous ether. Pretty much now, no matter how old it is, unless it's very new. The older anhydrous ether bottles have a metal cap on them. We don't even pretend. We save it for the bomb squad. It's just that simple. Just a rule, quick and easy. Newer solutions of peroxides have stabilizers in them. So for instance, seam sealers for tents have tetrahydrofuran, but they also have a stabilizer in it, which means it's not harmless because it's flammable as heck, but they're not peroxide formers. You should, if you deal with chemicals on a daily basis or almost daily basis, you should get yourself a list of what are called the Class A peroxide formers. It's worth becoming familiar with that list. There are no particular things I can tell you that always put something on that list. Other than that, they readily form peroxides and they're dangerous. Good list to have around as a quick and easy reference. All right, we'll skip this break because we just did it. Organic chemistry, which I know you've all been looking forward to. Organic chemistry in our little retro world, though, is important. We said that organic acids aren't as strong as mineral acids. That's true. But organics form the basis of a lot of explosives. They form the basis of a ton of poisons. And we can learn a vast amount about the chemical in question from its name, if it's properly named. There are trivial names of organic chemistry, and then there are formal names. Formal names can be almost impossible to read, but can tell you a lot. Trivial names, benzene is a trivial name, for instance, can still tell you a lot because a lot of them are very recognizable. Organic chemistry gets made fun of a lot by organic chemists, by everybody else. Until you take physical chemistry, you tend to think of organic chemistry as the worst course you've ever taken in your life. And until you take PChem, you're right. This is one of my favorite little cartoons. This one always reminds me of Babar the elephant, but all these things are true. Organic chemistry is about 4 things, really. I mean, there are lots and lots of other sort of bit players in all this, but the key elements of organic chemistry are carbon, nitrogen, oxygen, and hydrogen. Kind of in that order to some degree. Carbon can form 4 bonds. That is, if we go back to the very beginning of the class, it's got 4 holes left in its outer shell. Nitrogen has, where it's missing, 3 electrons in its outer shell. Oxygen can form 2 bonds because it's missing 2 electrons in its outer shell. Hydrogen can only form 1 bond at a time because it only is missing 1 electron. Again, it all comes back to the electrons. Everything about chemistry is about electrons. Finding the electrons is what learning chemistry is all about. Organic chemistry has wildly crazy combinations. They mean things, though, and we'll learn a little bit about them. You can intuit some things, and hopefully by the end of this, you'll be able to intuit a little bit more just from the structure or the name of organic compounds. Because they're so complicated, all this stuff. I was going to use a different word. Stuff over here. It's too complicated to draw out each individual atom in a molecule. So for instance, if we look at this drawing here, this thing labeled number 1 is exactly the same to an organic chemist, or to a chemist, I guess, as number 2. What we've done is eliminated the obvious, and this is by convention. There's no particular reason for it. Somebody decided, probably some German about 100 years ago, decided this would be simpler. And we've stuck with it ever since. The Germans did a vast amount of research in organic chemistry between the 1850s and the 1930s. They got to make a lot of the rules. Here we are. So anytime you see a corner in an organic chemistry thing, and there's nothing else there that's an H that's missing. So if we look at this corner is a C, it's a carbon. We know carbons can make 4 bonds. Here's one of the bonds here. Here's one of the bonds here. Here's another bond. This is a double bond. 1, 2, 3. We're missing a bond. It must be a hydrogen. Just that one right there. Same is true in this kind of a diagram. This is a hydrogen. 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 This one is not a hydrogen. That is 1, 2, 3, 4 bonds. This is 2 hydrogens, one coming up here, one coming down there. There's no hydrogen here because we've got this carbon, 2 bonds with the oxygen here, bond, bond. That's it. That's the secret to organic chemistry right there. You know how to read these little stick figure diagrams. You're done. You can walk away and say, I'm done. Anything missing will be noted. This ring here is called a benzene ring. Bromobenzene, you know it's a ring structure. We'll teach you some more about what ring structures mean. You know it's got bromine on it somewhere. Fluorobenzene, same thing. This is a little more complicated. Same kind of thing though. 2,4-dichloromethylbenzene. Benzene, we know it's got this trunk here. Dichloro. The 2,4 is going to tell us where these chlorines are in relation to this methyl group. This CH3 is a methyl group. That becomes, by convention again, not by any chemical reason, the number 1 position. The 2,4 in a clockwise direction are, this is 1, this is 2, 3, 4. You could theoretically have 2,5-dichloromethylbenzene. You could have 2,6. Those, in terms of where they are, matter, sometimes just for their chemistry and sometimes for their biology as well. These numbers tend to be important, and some of these words can be important. We'll get into that a little bit. Fast. All right, organic chemistry is, once you learn how to read the little stick figure diagrams, is all about functional groups. We're a touch pressed for time here because I talk too much. So I'm going to point out some that you need to know about, some that are worth, you don't have to memorize the structure of anything, but you do need to memorize the names of some of them. All right, ethers. Ethers look like this always. Remember again, where the R's are just other groups. Could be H's. Technically, water is an ether. Too complicated to get to. Ethers in and of themselves are not bad. They're flammable almost always. They almost always smell sweet, but they can form peroxides. Ketones almost always smell bad. Esters are almost always used in perfumes and things we want to smell good. Isocyanates. Isocyanates. This reaction group here with the N double bond to the carbon double bond to the O is a lot of concentration of electrons in this area and leaves itself very willing to have something like a ketone come around, attach to this oxygen, and then have another isocyanate attached to it later. Hazardous polymerization. I assume we all know what that means. These guys are the issue there. Thiol, you don't need to remember much except the phi, the THI, means there's sulfur involved. So when you read a label or an SDS, you're doing it because you're trying to find something out. Something that's aromatic will tell you that it's a ring structure, that it's one of these benzene kind of rings here. P, O, and M are called directors. What they're telling you is where the group immediately before it is situated. And they're shorthand for the 2, the 4, and the 6. Well, 2, the 4, and the 3, really. But so para whatevers will be like this. Metas will be like this here. This will be the 3 group. Flipped around, it's the 4 group. 1, 2 ortho, flipped around, it's the 5 group. Will be like this. So sometimes you'll see orthotoluene, chloroorthotoluene. That tells you it's a different way of saying 2-chlorotoluene. Just tells you where it is. Saturated, unsaturated, and polyunsaturated, we're all pretty familiar with this from fats and stuff. It's merely a question of how many double bonds there are in a long carbon chain. From a hazardous waste chemistry point of view, leaving aside the existential parts about your diet or my diet, not very interesting. Isomers. Isomers are tons of fun. They're super complicated. It just means that the atoms are arranged around one central molecule, which can be hard to find, in a clockwise direction versus a clockwise direction, a counterclockwise direction. Your body, strangely, can't always tell the difference or can't always use things that are in the counterclockwise direction. You'll hear about right-handed amino acids or right-handed carbohydrates or left-handed carbohydrates. Those are things where they're arranged in the other order, and sometimes your enzymes cannot recognize those, cannot use those. Sometimes your taste buds can, which is just weird. Furan and dioxin. Furan is not in my little chart here. Furan is a ring structure with an oxygen on it. It may be stable, but it has lots of energy in it, lots of things that are explosives or furans. Dioxins are multi-ring structures generally and tend to be very stable and bioaccumulate. They're not generally acute poisons, but they are long-term poisons and hugely carcinogenic. Almost every dioxin is carcinogenic. Fulminates. Fulminates are bad. Fulminates mean a triple bonded, or at least a double bonded with something else nitrogen. Fulminates are inherently unstable, almost always shock sensitive explosives. Do not handle fulminates, do not accept fulminates. Fulminates are a call to the bomb squad. There's nothing good about them. I mean, there are a lot of good things if you want to blow shit up, blow stuff up. But from the safety point of view of our techs, ourselves, and public, not good. Metha, etha, propyl, butyl, these are all ways, shorthand ways of counting in organic chemistry. Meth means one carbon, eth means two carbons, and so on. Goes on for a very, very long time. Aromatic things have a ring structure. This ring structure contains a lot of energy, but is fairly stable. But it does mean that it'll burn easily. Benzene is composed of a lot of things with a lot of this ring structure. Naphthalene, for instance, has a lot of ring structure, a lot of energy. Here's a furan, a lot of energy, a lot more energy because these bonds here are unnaturally tight. Well, can't be unnatural because they exist, but they're tighter than thermodynamic stability would like them to be. Things with more than 6 carbons in them are not aromatic, or 6 carbons in the ring. They're also not natural. They have to be created. You won't see them. It's just a counterexample. It is what it is. Directors we went over, I don't think we want to spend a whole lot of time on them. Saturated, unsaturated. Isomers, like I said, are fascinating, but we don't, it's a biological question, biological function question only. Tons of fun, tons of time to spend on them. Furans and dioxins are toxic, flammable, carcinogenic. They're almost certainly regulated at one level or another. If any of those words are in them, you're not going to throw them out as non-rec or waste. You're going to have to figure out something to do with them. Fulminates are another word that I'd love you to take away with from this class and say, Michael said something about fulminates. It was really important. What the heck was it? I'd love it if you remembered that they were shock-sensitive explosives. Rather just, well, not rather, but I'd also like you to remember the word fulminate means unstable, means explosive. Mercury fulminate was used as a primer for a long time. It's kind of the classic fulminate. It is, however, corrosive as well as being shock sensitive. So after a while, the percussion caps in old ammunition would start to go off, not quite on their own, but pretty easily. This was unpopular with soldiers, so they came up with something else. Potassium chlorate, if you're interested. Basically, organic chemistry is not, they're about organic acids. They tend to be weaker than, they tend to be non-recur acids. We tend not to worry about them. They have, the carboxylic acid has a functional group as an acid, but it's in relation to how it's reacting with other organic chemicals. Sulfur means thio. Halo always means one of the halogens. Halogens tend to get treated differently by our environmental quality departments. So they often want to know if you have halogenated something. The halogens will either say it's halogenated or they'll say bromo, chloro, or iodo. Iodo's rare. Chloro and bromo instantly tell you that whatever you've got is halogenated. They're almost always toxic. They're often biopersistent. Nitro groups are another one that are worth remembering. They're very reactive. The more nitrogens there are in a word, that is, if it says dinitro, that's better than this nitro. Trinitro is worse than dinitro. The more nitros, the worse, the more likely it is to be an explosive. TNT, for instance, stands for trinitrotoluene. So for instance, nitrotoluene, 4-nitrotoluene, again, this just tells you, you can't see that, tells you where the nitrogen is on that toluene, which is a benzene derivative. Okay, a little bit corrosive, little starman here, don't drink it. 2,4,6, trinitrotoluene, explosive. Not going to really worry about this. But we are going to worry as heck that it's explosive, and it's a 1.1. Esters, not very interesting. They make things smell better. Ethers are highly flammable, have very high vapor pressures. Not so much an issue there, except that they can form peroxides. So an old ether is way more worrisome than a young ether, a new ether, probably a better way to put it. All right. If chemistry existed and it looked like this, where everything was in secondary containment, where it was neatly labeled, we wouldn't have jobs, or at least I wouldn't. Or if behind glass containers, or this. Unfortunately, chemistry, at least in our facility, looks a whole lot like this. Old bottles with some part of the label, and the rest that you really can't read very well. So what I'm trying to teach you guys about the organic chemistry part is this word here is B-U-T-Y-L, vinyl. The rest was missing. This tells you that it was butyl vinyl, almost certainly ether at the end of it. The bottle's in horrible shape. Time is not good friends to these things. And this is a mass of crystals right here inside the bottle. We didn't open this. Here's another version of the same kind of thing, but with a better label. Tells you it's an ether. Tells you which ether it is. Bottle's in pretty good shape. There's no visible crystals inside there, but there's a number of crystals leaking out here. I wouldn't open this to save my life. This is all from one load, by the way. Big kind of 5-gallon thing of ether here. It says ether over here. Because I am what I am, I sloshed it around a bit, didn't open it. Didn't sound like ether, didn't feel like ether. Abundance of caution. We called the bomb squad. We did a peroxide test on the opening. We weighed it to see if the density matched something that would be ether. It didn't. It was a little bit too heavy for that. Finally, the bomb squad guy and I flipped a coin to see who got to open it. It turned out to be oil. Pretty good. All these things are organic chemistry gone wrong, that you'll want to pull up some sort of reference to the words that I've been telling you about to say, okay, what did that mean? What should I do? All right, SDS and GHS. I'm sure we all know how to read an SDS and a GHS at this level in our lives here. Those are not the right pictograms, but they are kind of funny. These are all things we've talked about to some degree. Oxidizers can burn on their own. Corrosives can damage skin or metal. Gases under pressure, we didn't talk about. These tend to be a mechanical danger rather than a chemical danger. Flammable, you guys know all these. Hazmat placards, if you don't do shipping for a living, you may not be as familiar with these. These are all, or have all, counterparts in the GHS world. GHS is more of a, not quite, but more of an end user explanation. Hazmat placards are a DOT, Department of Transportation explanation. They often mean exactly the same things, and you'll see things with both of them on there. I think it's worth, for any HHW work, it's worth being familiar with these as well as these. The chances that you're going to get something that comes in with a perfect GHS label all the time is pretty low. Hopefully, if it doesn't have a GHS label, it'll have some sort of dot placard. If it doesn't have a dot placard, hopefully it'll have GHS. Years ago, I think it was 6 years ago now, SDSs or MSDSs became SDSs. From my point of view, this is an unalloyed good thing. We don't have to search around for everything. All the things, if I want to know about accidental release, it's in section 6. It's not somewhere else, it's only in 6. 10 is reactivity, 11 is toxicology, all those kinds of things. GHS, as I said, tends to be the end user, tends to be a question about long-term exposure. DOT is what happens if there's an accident. It's the short-term exposure. What's the danger right now and how should we respond to it? Toxins and poisons are interesting in both of them, and it's worth learning more about, darn it, section 11. Section 11 can be hard to read. It's very jargony. And this takes us out of the chemistry bit a little bit, but it stays within the biochemistry, so I'm going to call it good. The toxicology parts will have a whole bunch of things in there, but the two most important parts they'll have are an LD50 and an LC50. LD50 stands for lethal dose. LC is lethal concentration. They can be of a toxin, radiation, a pathogen. It's the dose required to kill half the animal population used. LD is a dose that they administered to them. LC is a concentration in the environment they had the animal. These will have to be, on any reputable SDS, followed by the animal model they were in. Environmental or long-term environmental stuff is generally done in fish or in some insects. That's a question for your packaging, for your disposal, water quality issues, Clean Water Act, all that kind of stuff. Those are important, and those are telling you about water. LD50s and LC50s are telling us sometimes about their immediate lethal effects. The bigger the number after this, so a lot of them will say something like LC 55 milligrams. That's a very small number. That means that you're dealing with a poison by inhalation, almost certainly some nerve gas or some nerve gas derivative, and you should wake right up and pay attention. LD50, LC50 of 5,000 milligrams is telling you, okay, this may cause cancer, may cause all sorts of things, but it's not an immediate danger to life and health. GHS stuff tends to focus on, I think of long-term, I think of immediate as right now when I'm on a response, but it is immediate in the sense of the day or two. DOT doesn't care whether something's going to cause cancer. It doesn't care about germ cell mutant immunogenicity. It cares a little bit about skin sensitization, doesn't care about reproductive toxicity. GHS is going to tell you all that stuff. If you need or want to know about these things, you're going to have to look at the SDS. Nothing in the hazmat table is going to tell you any of those things. The chemistry sections, as it were, the parts we're interested in. Section 1 and 2 are surprisingly useful. They will have the name, which you can read into a little bit. It'll also have synonyms. And often the name that the manufacturer is using is not the most common synonym. There may be reasons of their own for that, but they'll have to list all the common synonyms. Section 9 is really kind of what we've been talking about. It's things like the pH, the boiling point, the flash point, the molecular formula. If you can look at it and say, oh, it's one of those nitro groups Michael was talking about. Boiling point can all tell you various things. If we had another hour and a half, we'd go over it in detail. Section 10 is interesting if you're worried about anything mixing. These are incompatibilities. These are if you have a leaking container and you're worried about putting it next to something else, this is the section you want to look at. Section 14, we use a lot, even sometimes just for basic ID, to give us an idea of what the proper shipping name looks like. And that kind of helps us fit it into a category. Obviously, it gives us a shipping category, but it can tell us a little bit about any incompatibilities. For instance, if it's listed as an inorganic acid, we know we don't know which acid it is, but we know we don't want to put it next to a base. A couple of examples. Some of these are extreme. Some of these are just interesting. And I think we have time for them. Picric acid. We're all scared of picric acid. We all should be. It doesn't tell us much. It's what's called the trivial name. These are the everyday names for things. However, if I said it was 2,4,6-trinitrophenol, and you just listened to me say something about more nitrogens are bad, you would say, okay, I know where those nitrogens are. I know there's 3 of them. I know that tends to be explosive. And look at all those other things with nitriles on them that are explosives. Top 3 are kind of your common explosives. These are military explosives. They all have a lot of nitrogen groups on them. A lot of NO2s here. None of these are all manufactured. These are all military explosives. Should you see any of these, you need to call the bomb squad. I would argue you should call the bomb squad with these too. But this is ordnance. There's probably more than the bomb squad involved if you see those. Picric acid has been used for all sorts of bizarre things. It was used prior to World War II as a burn dressing. You will see it sometimes in old Girl Scout and some old Boy Scout, more Girl Scout, first aid kits. It'll be dry, it'll be a shock sensitive explosive, and you will probably want to call the bomb squad. If you get dry picric acid and you're inhabiting a world where you feel it's okay, and I urge you to be very, very careful about this, our bomb squad requires, because they have faith in us, that we rehydrate it. We try to do that very, very carefully. Literally, we don't open the container, put the container in some water, put a brick on top of the container, and let it go for a couple of weeks while the water works its way through the threads. Should something like this, yellow, with some reason to believe it's picric acid with these long feathery crystals, these are distinctive, come into your facility or you find it in a facility, this is almost certainly peroxide crystals in picric acid. These are shock sensitive explosives. You need to back away. If you need a photograph of this, you need to take a non-flash photo. It's not true of all peroxide crystals, but it's a better rule of thumb than doing it the other way. Things like these have caused huge explosions in industrial settings. This is just an old one that's not even quote unquote all that bad. Perchloric acid years ago, this is 1947 in LA. They were cleaning aluminum furniture with perchloric acid, and somebody somehow, nobody knows why because they didn't survive, dumped some of it into a vat of sawdust, blew up and killed 47 people, leveled the whole block of LA. All because this is a super acid with a, if it had a pH, it would be something like minus 14 or 15. There's a pKa of like minus 18. It's got a ton of oxygens here in these bonds. They're double bonded. It's an oxidizer and an acid. Sawdust was like the perfect thing to dump it in. Careful. Hydrofluoric acid. This is my pet peeve. Peeve is the wrong word for it, but this is an acid that you will not always know you've spilled on yourself. As horrible as these burns are and look, this is not what will kill this person. probably a guy. What'll kill him is the fluorine binding ionically, but still taking it out of solution to the calcium and magnesium that his heart and nerves need to work. Quick run through the fundamentals. Chemistry is all about electrons. It's all about electrons. Nothing else matters. We're not going to change any of the elements into anything else using chemistry. If anybody says they can do that, more power to them, but I'd be very skeptical and I wouldn't invest a whole lot of money. Periodic table, my personal feeling, absolute work of genius. Dmitry Mendeleev was one of the geniuses involved, but it's amazing. Chemicals combine in chemical reactions. They also separate in chemical reactions. Covalent bonds are relatively strong. They take energy to create, they take energy to break. Acids, as we know, have a pH below 7. Bases have a pH above 7. They're both dangerous if they're high enough pH. Mineral acids, names tend to be shorter. They tend to be stronger. Oxidizers and peroxides, I don't think we need to know more about ammonium nitrate than this explosion in Beirut. That was insane, utterly crazy. Organic chemistry, super complicated. Functional groups are important. Nitro is explosive. Amine, higher pH. Carboxyl, lower pH. Thiosulfur, ether, furan, dioxin, fulminate. Pay attention, all for different reasons, but pay attention. Water is awesome. It really is. I mean, water is one of the coolest things there is, chemistry. And that's all I've got, and we made it, just barely. That's my work number. It's not a desk number for me, the 503, which you guys can't see when I point. It is the facility number, but if I'm there, it's the way to get to me. I generally don't answer my cell if it's an unknown answer. You are happy to message me with a question if you don't want to email me. LinkedIn stuff. I copied this out of LinkedIn. I don't use LinkedIn a whole lot, although I've started. So I think this gets to me. And that's it. That's